and we're going to be studying PySpark together. Apache Spark is a fast and general engine for large-scale data processing. With it, you'll be able to easily write data processing workflows that run over tens or hundreds of computers. You'll be able to apply distributed machine learning algorithms or run low-latency stream processing topologies. Spark is an exciting technology and the heir apparent to Hadoop, the distributed processing mainstay. This course is going to cover both introductory and intermediate level PySpark usage. Although I'm covering the material using PySpark, the Scala and Java APIs are quite similar, and you should be able to apply knowledge from this video series in either case. I assume no Spark knowledge, but you will want to have a working understanding of Python. What will we be covering in this course? First, installing Python and Spark. Then, Spark fundamentals, such as what is an RDD, or how do I get data in? Next, we'll look at transformations. What are some of the most commonly used transformations in Spark? And how can I use them better? What are some extra options that we might already know about? Then we'll look at actions, some of the most important actions in Spark. We'll review key-value pair RDDs. They provide functionality like joins between datasets, or aggregating over subsets of your data. We'll also cover input and output, some of the most common ways to read and write data in Spark. We'll cover performance. These are some advanced Spark features that will help with performance and also workflow metadata generation. We'll look over what it takes to run your PySpark workflow on a cluster. We'll look in particular at the Standalone cluster, a Mesos cluster, and a Yarn cluster. Finally, we'll have a brief overview of some advanced Spark topics. Those include Spark Streaming, Spark SQL, and MLlib. I hope you're as excited as I am to check out how Spark can make distributed processing straightforward and fun. This video is going to cover Python, installing Python, and a useful tool for why you're using Python. We have to install Python because PySpark, the Python interface for Spark, uses Python. So what is Python? Well, Python is a high-level programming language. That means that in general, you'll write fewer lines of code in Python than you would in Java or C to solve the same problem. Python is an interpreted language, not compiled, so there isn't a separate compilation step before you can run your code. Python is dynamically typed. That means that you don't have to provide types for your code that's worked out by the interpreter at runtime. Python has an emphasis on readability. The designers of Python work hard to make Python code easy to read and easy to understand. In fact, you'll see that it's almost the same as the pseudocode that you see in a lot of programming textbooks. Python is also very popular with the scientific programming community. They use packages like NumPy, SciPy, PyLab, and Pandas to do all sorts of data analysis and math from the comfort of Python. Python also comes with a REPL. If you've never used a REPL before, I think you're in for a treat. I'm going to give you a quick demo because I think that REPL programming will change the way you think. To start the Python REPL, just call Python with no arguments. REPL stands for read, eval, print loop. So if we type some code in and hit enter, Python will read it, evaluate it, print the result out, and then loop back, waiting for us to provide more input. This kind of real-time feedback is significantly faster than waiting for your code to compile and run to check if something's right. This is a great way to explore a new library or check to see what the array slices should be when you're trying to slice just the right number of letters off of a string. Assuming that you're as excited about Python as I am, you're going to want to know how to download it. Here at python.org, if we scroll down to the download section, there are two different versions. There is a Python 3.5 and a Python 2.7. For Spark, you need to download Python from the 2.x line, not the 3.x line. Spark doesn't yet work with 3.x. So if we click on Python 2.7, they have many different files. So depending on your operating system, you'll need to pick the appropriate file and follow the installation instructions. Once you have Python installed and running, you'll also want to look into virtual environment. As it says here, virtualenv is a tool to create isolated Python environments. By default, Python installs all of its packages into a global site packages directory. While that solution is simple, it runs into problems as soon as you have two projects that need different versions of the same dependency. To work around that problem, lots of Python developers use this tool, Virtual Environment. This allows you to create isolated Python environments that each have their own site packages folder. In the same way that most programmers have moved away from using global variables, most Python developers have moved away from using a global site packages directory. Installing virtualenv is simple. Click on the installation link on the left, and then scroll past all the warnings. You can see that right now, the recommended way to install it is with pip. Pip is a Python program that installs packages. Pip stands for Pip Installs Packages. If you've installed one of the more recent versions of Python, you probably already have pip. If you don't, go ahead and Google it. It's easy to install. Once you have pip, you can just use sudo pip install virtualenv and wait for it to download and set up virtualenv. Now let's look at how you would use virtualenv to create your isolated Python environment. To create an environment, use the virtualenv command followed by the name of the environment you want to create. For example, I'm going to create a testenv virtual environment. This is going to show up as a folder in your current working directory. Now let's check that it did indeed make a folder, and it did. If we move into the folder, we can see that it has created a couple of folders for us inside it. Before your virtualenv is activated and working, you'll need to use the activate script located inside bin. You can use it like this. You can see at the beginning of my command prompt, testenv is surrounded by parentheses. That shows that it has been activated. Here you can see that the Python executable I'm using is coming from inside my virtual environment. That's going to help me get a separate view of my packages from other virtual environments. Okay, that covers installing Python and installing virtual environment and a little bit of how to use it. This video is about IPython and Jupyter. You can install IPython using pip. I would recommend also installing it within a virtual environment so you won't be affecting the system Python. Let's see how to set up a new virtual environment and then install IPython into it. First, we'll make the new virtual environment. Way you do that is by calling the virtualenv command with the name of the new environment you want to create. Once you've created your virtual environment, you need to activate it. You do that by sourcing the activate file within the bin folder of that virtual environment. Now you can see at the beginning of the line, it says IPythonEnv. We named our virtual environment IPythonEnv, and it's been activated. Now we use pip to install IPython. It takes a couple seconds, but we should now have IPython. We can test it out by calling IPython from the command line. What is IPython? IPython is an improved Python REPL. It has input and output caching, so you can easily reference previously entered or output values without retyping. This can save a lot of time while interacting with your work. IPython also contains parallel programming tools that can help process larger blocks of data across multiple cores or over MPI. Here at the prompt, I'll show you a couple of other neat features. First, there's tab completion. Now I've made a long variable. Instead of having to retype the entire thing every time, I can just start typing and then hit tab. Now I'm going to use the input caching. You can see next to each of the in lines, there's a number, so I can use that to reference one of the previous lines. You can see here that in1 was the string my_long variable equals 1. You can do the same thing for output. If I wanted the output from line 2, I can get it like this. There you see the output from line 2 is 1. You would more often use that maybe as the input to another function, for example, something like that. IPython also includes an inline help system, which can be really nice. If you type the question mark once, you can see a lot of help documentation from the IPython terminal. As you can see at the bottom of this help document, typing $word or word question mark gives you some information, where question mark word gives you access to a whole lot of help information. Let's see how that works. Here you see that question mark map gave us a doc string and some type information. In this case, question mark was the same. That's due to it being a built-in function or method, so there's not a lot more to show. Another interesting feature of the IPython REPL is the debug help. Here let's simulate an exception that you might see in a program. Here, I set a variable equal to 0, and then I tried to divide by it. Clearly that's not going to work. In general, your exceptions are going to be a little bit harder to find, but let's use a simple one like this just to test out some of our tools. IPython provides a debug command that lets us go into the Python debugger and debug the last exception that was thrown. By calling debug, we've entered the IPython debugger. The IPython debugger is a wonderful software tool. If you don't know about it, you should put in some time to learn. I'm sure that you'll be happy you did. I'll go over just a couple of the commands that you use in the IPython debugger. The first is H for help. Next, W for where am I? This isn't that informative here because we were just typing from the REPL, but if you had been using source code, this would show you where in the source code call stack you were. P prints out a command. Here we see that we were doing 1 divided by x. Let's figure out what x was. We see that x was 0. Well, if we're dividing 1 by 0, that's going to be a problem. Now that we've figured it out, let's use Q to drop out of the debugger. You can also use the magic command %pdb. %pdb will automatically drop you into the IPython debugger as soon as you encounter an exception. Let's divide by 0 again. And there we go. We are right in the IPython debugger. Interactive debugging with the Python debugger is a great way to figure out what's going on inside your code right where the exception is happening. This will save you a lot of time and is easier than putting print statements everywhere you think there possibly could be a problem. Finally, we'll be looking at the most useful part of IPython, in my opinion, the Jupyter Notebook. Jupyter allows you to create, save, reload, and edit a programming session. It's similar to a REPL, except that you can go back in time and edit previous commands. This allows you to tweak your process while developing it. Then share it with a colleague without hiding the work you did to find the final output. This is hugely useful for repeatable research, as well as sharing code between coworkers. For example, you could create your work presentation in Jupyter, then tweak it live based on input from the audience. You can install Jupyter with pip the same way we installed IPython. Here you can see I'm still in my IPython virtual environment, and I'm just going to use pip install Jupyter. So Jupyter has finished installing. Now we're going to start it up and look around. So when you call it with no arguments, it shows you the help message and that it expects at least one argument. The one that we'll be using now is the notebook function. Jupyter is a server, and it lets you run interactive programming sessions on it. Right now we don't have any running. Let's make a new one. Here we have a brand new untitled Jupyter session. Let's give it a title. So in a Jupyter session, you can type code in and evaluate it to get results out, just like a REPL. Here I do Shift-Enter to evaluate it. The exciting part about the Jupyter REPL is that I can go back and change my previous line and see the new results. I can also save this and then reopen it. Now I'm closing it and now reopening it. And my work's still there. I can share this with other people through the URL, assuming that Jupyter is running somewhere that's globally accessible. So Jupyter has Markdown support and also multi-kernel support. So right now, and for the entirety of this course, we'll only be using it with Python, but you could also use R, JavaScript, my personal favorite, Clojure, Scala, Ruby, Go, and many others, over 40 languages. That's all for now. I hope you're excited to use Jupyter and IPython as we explore PySpark. This video is about downloading and installing Spark, as well as a little bit of historical context. First, downloading Spark. You can find Spark at the Spark homepage, spark.apache.org. Follow the download link, and scroll down to see the options. In this case, we want the most recent release. Choosing a package type will determine which version of Hadoop your Spark will run with. If there's a Hadoop cluster that you know you'll be running on, you should check with your administrator to find out what version of Hadoop is running there. I know that I'll be running on a Hadoop 2.6 cluster, so I'll choose that. You should use the Apache Mirror to save some money for the foundation. Now we're going to click on the link and let it download. This is about a 300 megabyte file, so it'll take a little while. Also, it's a gzipped tarball, so you'll need to use tar to extract it. Let me show you how that would work. Here you can see I've already downloaded the gzipped tarball Spark 1.5.0 bin Hadoop 2.6.tar.gz. I'm going to use the tar command. I'm going to use the flags xzf. X means extract, Z means that it's gzipped in addition to being tarred, and F means that I'm about to give it the file I want it to work on. So tar, xzf, and then the file I want. Now we'll check to make sure it worked. There it is, Spark 1.5.0 bin Hadoop 2.6. Spark really is that easy to install. I figured we'd take the rest of the video and provide a little bit of context for the distributed processing world and where Spark fits in. Spark is a general computation engine that makes it easy to write jobs that run on more than one computer. But why is that important? What problem does it solve? Well, we're getting more data all the time. Data sizes are increasing much faster than processor speed. They're even increasing faster than the number of cores. We have two options. Option 1 is to spend lots of money on big iron, a single super fast, super expensive computer. The more data you get, the more computer you have to buy. The cost of the computer increases more quickly than the size of the data. You're going to run out of money before you run out of data. The second option is buying many commodity computers and running your job across them. This choice led to Google's seminal MapReduce paper. MapReduce is a processing framework that allows you to run large processing jobs on unreliable commodity hardware. Yahoo created and then open-sourced an implementation of MapReduce that's now known as Hadoop. Hadoop has served, and continues to serve, as one of the workhorses of the big data revolution. However, some problems don't fit the MapReduce paradigm. Some problems are slow in MapReduce. Some are so slow that they might as well be impossible. Spark started as a research project in the AMP lab at UC Berkeley and has grown into an open-source Apache project. Spark attempts to address some of the shortcomings in Hadoop. It's a more general-purpose solution. It can operate according to the MapReduce paradigm, but it's not limited to it. Additionally, because it works to keep data in memory and combine compatible steps, it can be significantly faster than Hadoop for some types of workloads. Spark is also, in my opinion, easier to work with than Hadoop. You write higher-level code in Spark, which often makes you more productive. We'll have plenty of time to see what makes Spark so much fun. I hope you're as excited as I am about this powerful tool and the huge amounts of data we'll process with it. In this video, we'll learn about the PySpark REPL. There are actually two Spark shells, the Scala shell and the Python shell. We'll only be covering the Python shell in this course, but if you're familiar with Scala, you might want to check out the Scala shell. The Spark Python shell is just like the normal Python REPL, but with a connection to a Spark cluster underneath. Developing with a REPL is great for exploring and playing with your data. You can get real-time feedback. Because the Spark shell is a REPL with a real Spark cluster behind it, you can do ad hoc explorations of large amounts of data. Let's take a look at a simple Spark workflow. You probably aren't going to understand what's happening here, since we haven't studied the Spark API yet, but don't worry, we'll cover it all in detail later. Note that you start the Python shell with the PySpark script. I'm in a folder that has two directories. The first, PySpark, is a virtual environment. Let's activate that first. Now we can tell that the virtual environment is activated because of PySpark to the left of my prompt. Now, to start the PySpark shell, I'm going to use the bin/PySpark inside the unzipped Spark directory. Here you can see that we started up a lot of Spark services in the background. That's where all that logging came from. Once all that started, we're dumped into a normal Python REPL, but with one important difference. You can see it as the last line before the prompt here, Spark context available as SC. That SC is our gateway into all of the Spark functions that we're going to be using. I'm going to demonstrate a small workflow, and it's okay if you don't understand it yet. I'll talk through it as we go, and later on, we'll learn everything that you need to know to understand this. First, I'm going to create a Spark dataset. What that line did was take range 10, which is going to be the numbers 0 through 9, and send it out to the Spark cluster. It sent it out with the name numbers. Now I can do operations to numbers, and those will happen out on the Spark cluster. For such a small dataset, this is kind of pointless, but you could use exactly the same code on a significantly larger dataset. I'm going to increment each of the numbers by 1 and then pull them back into the REPL so that we can see them. Now I have incremented, which is numbers that have had 1 added to each number. Now, to pull it back into the REPL, I need to collect it. You can see that nothing happened until we asked for some information back. That triggered both the map and the collect. You can see the last line here that we got 1 through 10. That's the same as our input data, where each value was increased by 1. Obviously, that is a very simple demo. There's no reason that you would use a Spark cluster to increment 10 numbers. You can do that locally just fine, or even in your head. However, the power here is that by changing just the input and output functions, we could have run that same function across gigabytes of data using hundreds of machines with the same code. We could do aggregation and pull the results back in real time. We could see an interesting pattern and check it out in real time. I think this is really exciting. You are able to coordinate work on a huge production-sized cluster in real time from your laptop. This is game-changing for data scientists. You aren't going to need to do your initial exploration on a small sample, then hope that your sample was representative. You can do your work on the whole dataset. Let's look at a couple of settings you'll need to know to get the most out of PySpark. First, the master setting. The master setting tells the shell what Spark cluster to connect to. This is how you connect to your company's Spark, Yarn, or Mesos cluster. This is also where you can do a little bit of configuration if running in local mode. We'll use local mode for most of this course. There are a couple of valid local modes. The first valid local mode is just local. You would use it like this. Another valid local mode is local k, where k can be any number, for example, local 2 or 3. The first local mode, set it to one worker thread. This sets it to however many worker threads you want. You can also use local star. That sets it to as many threads as there are logical cores. In general, local star is a pretty good default when you're exploring. That's the default master for the PySpark shell. We'll cover the other master settings later in the course when we talk about how to deploy to different clusters. In Spark, there are two places code can run, the driver and the executors. The driver is the control software. In this case, the shell is the driver. Once you give a command that requires action, the driver assigns work to the executors. They each load data and perform the work. This architecture allows the driver to issue orders to many executors without all of the data needing to pass through the driver, which would quickly become a bottleneck. When using the local master, the worker threads act as executors. When running on a cluster, you can explicitly ask for a certain number of executors, so that you can control how many machines are working on your task. Since many Python scripts will require access to Python libraries, you'll need to make those libraries available on the local machines. You can either install the packages on all the executors, or use the PyFiles option to add files to the search path. If you're going to use the same libraries over and over, installing them on each of the executors will save data transfer. It'll be one installation instead of being transferred every time you run a job. However, if the required libraries change often, or are incompatible between jobs, you're better off adding them to each job as PyFiles. In this video, we'll be learning about using the Spark shell with iPython and Jupyter. First, a terminology note. Originally, notebooks were a feature of iPython. However, as notebooks began to support more languages, it made sense to make them their own project. That project is named Jupyter. Because my brain doesn't update as fast as their project moves, I'm likely to call them iPython notebooks or Jupyter notebooks or some combination of the two. Don't worry about it, those all mean the same thing. Jupyter notebooks are awesome. PySpark is great. Using them together is wonderful. Some of you might be familiar with RStudio's R Markdown format. It allows you to release your calculations and your findings all together. That's great when you want to make your work easily repeatable. That would be useful if you're an academic and you want other people to repeat your research. It's also useful if you're a programmer and you want to be able to share your work and have other people build on it. Jupyter goes one step further and allows you to edit and update your notebook, seeing the results in real time. I think quick feedback is so important. Anytime I have to wait longer than about 30 seconds, I'll pop open a tab in my browser and read XKCD. 10 minutes later, I'll remember that I'm supposed to be working and head back over. At least for me, any delay turns into a long delay. I'm going to show you just how easy it is to do a little bit of exploration in PySpark using a Jupyter notebook. Here you can see that I've already activated my PySpark virtual environment. This virtual environment has IPython and Jupyter already installed. The command line invocation to start PySpark with IPython and notebooks is a little involved, but we'll go through it one piece at a time. I know it's a little intimidating, but stick with me. First, we're setting the PySpark driver Python to IPython. That means when PySpark starts up, it should call IPython instead of Python. Next, we set PySpark driver Python ops to notebook. That means when PySpark starts IPython, it tells it that it wants it to be in notebook mode. The last part is just me calling PySpark. I unzipped the Spark download into the Spark 1.5.0-bin-Hadoop 2.6 folder. So then I call into the bin PySpark executable. Great, it worked. Here is Jupyter, and we can see that we already have a couple of notebooks that I set up earlier. Let's look at the PySpark sample. Now, you're not going to have this. I set this up myself. I'll also change the view so that things are a little bit bigger. Okay, I'm going to talk through each line and then execute it so you can see what happens. First, I'm going to import cycle from itertools and add from operator. Cycle is a function that produces a generator that alternates between its input values. In this case, it will alternate between even and odd, because that's what I call it with later. Add is just a way to access the plus function as a function instead of an infix operator. In the next line, I'm making a sequence of even and odd paired with the numbers from 0 to 20. Now, let's look at the first three values in n. That's a little weird looking though. I must have made a mistake when I was entering stuff earlier. But I can fix it because this is a notebook and they're editable. Okay, here you see it's even, odd, even. Keep in mind, I was only looking at the first three because I did a slice notation there, but there are actually 20 things in this list. Now, let's put n into Spark. We'll do that with the next line, sc.parallelize. Remember, sc is the Spark context. This is how we get into Spark. When you run PySpark, the main thing that it does is provide this sc, which is a connection to a Spark cluster. Now, let's add one to each of the values. Notice I was using the Python lambda syntax that allows me to do a short inline function definition. I could also define that function somewhere else and provide the name here. Next, I'm going to reduce all of the keys. What that means is that I'm going to add up everything that has the even key and everything that has the odd key. So I'm going to add all the even numbers together, and I'm going to add all the odd numbers together, but I'll keep them separate from each other. Now I'm going to collect that and bring it back to the REPL. Here you see adding all the evens added up to 100 and adding all the odds added up to 110. So that's how easy it is to create data, push it over to Spark, operate on it in Spark, and then pull it back into the REPL. Lastly, I want to show you how easy it is to include plots and charts. You'll want to install the excellent MapPartitionLib package using pip. I'm going to show you an example that I put together earlier. This is just a brief overview. I'm not going to go into any depth about NumPy, Matplotlib, or PyLab. Those are all great projects and are well worth your time if you're interested in them. There's just no way I can do them justice and also cover PySpark in this course. Again, I'm going to close some stuff so that we have more viewport space. The only parts of this demo that I really want you to understand are the first part and then seeing the graph show up, so I'm going to move pretty quickly. First, the PyLab inline. Executing this is what allows the images to show up inline. If you miss it, things are not going to work the way you hope. The next part imports everything that the rest of my code will use. PyLab, that I'm importing here, is a module from Matplotlib. It attempts to create a MATLAB-like interface for Python. NumPy is a library that gives you a lot of numeric tools for Python programming. We've already seen itertools, cycle, and the operator add from the earlier example. What I'm doing in the next part is creating another even-odd data set, reducing it by key, and then collecting it. So this is round-tripping through Spark and then coming back to the REPL. Once it's in the REPL, I used NumPy and PyLab to make a graph of it. This might not be the best graph, but I think you can see the power here. I'm creating graphs inline with data that went all the way through Spark. I could use a large Spark cluster to create aggregated data over many terabytes of input. With enough computers in your cluster, you could do this quickly and easily. You could do it in almost real time over terabytes of data. Hopefully that gives you a small taste of graphing in your notebook. There are many, many other kinds of graphs. Please don't take the ugliness of this graph as an indicator of how your graphs have to look. That's more an indicator of my laziness. There are several galleries of what's possible with Matplotlib and PyLab, and you can make some truly beautiful visualizations for your data. In this video, we're going to cover resilient distributed datasets. In Spark, all data is stored in a resilient distributed dataset, normally called an RDD. The easiest way to make an RDD is with the parallelize command. Here's a short demonstration. So I'm going to call parallelize on the Spark context that's provided by the PySpark shell, and I'm going to pass it a data structure. In this case, it's a list with the numbers 1 through 5. I'm going to take the result of that and store it into the variable RDD. We've stored it into the variable. Now I'm going to evaluate that so you can see what's in it. Okay, here you can see that we have a parallel collection RDD, so a special type of RDD. So what we did here was take this list of 1 through 5 and turn it into an RDD that now lives on the Spark cluster. So you're probably wondering, Python already has data types like lists and tuples. Why bother with another data type? We're getting more and more data all the time. It's now very common to have more data than you can fit on the hard drive of one computer. So you spread the data out to multiple computers. However, once you start to spread it out, you have to deal with failures. If you have just one computer, the likelihood that it will experience a failure during your task is low. However, if you have many computers, the odds that at least one will have some kind of problem go up until it becomes almost certain. Let's look at some of the math behind this. Let's assume that your mean time to failure is 1,000 hours. So you can run your computer for 1,000 hours before you get some kind of failure. That might be you have a little bit of bad RAM, or the power cycles for some reason. Maybe you don't have really reliable power. It could be anything. 1,000 hours divided by 24 hours in a day means that you would have 41 days of computation per failure on average. So that means once every month and a half you would come in and the job that you had running isn't going to work out. You'll have to restart it. That's frustrating, but once every month and a half, I might be able to live with that. Now, instead of one computer, let's imagine a cluster of computers. 200 computers in your cluster. So if they have the same mean time to failure, 1,000 hours each, how long can you go before you have a failure on average? So here the math that I'm doing is one failure for every 1,000 hours, 200 computers doing that, and then I'm also doing the hours to days conversion. And here you're going to see that you have 4.8 failures per day when you have 200 computers running. This may or may not be surprising to you. The math is pretty straightforward, but I think it becomes apparent that when you have a huge cluster, not only can you do more calculation in parallel, but you can have more problems in parallel also. So your cluster is 200 times as good at producing failures as your single computer was also. Smart programmers often wonder why distributed processing frameworks are so complicated. It's a lot of tough work dealing with failure in a distributed system. Having a system like Spark that takes care of this for you will save you a ton of time. The extra complication up front makes things simpler in the long term. This is where the RDD abstraction comes in. The DD in RDD is pretty straightforward. Distributed means that the dataset is spread all over the cluster. Many different servers each have a part of the data. The second D in distributed dataset just means dataset. I don't think we probably have to explain that. The more interesting part is the R, for resilient. RDDs are fault tolerant. If one of the executors that holds a part of your RDD fails, the data can be recreated. Each RDD remembers where it came from and knows how to recompute part of its data if it's lost. This property saves a long-running job when one of the many computers involved has some kind of failure. For example, let's look at the results from a sample workflow. So here, this is the RDD we made earlier. Let's say that I decide I need to double all of the numbers in my RDD. I have my new RDD doubled. Here we can look at it. And we can even look at it to check that it remembers how it was created. Here you can see that it knows that it's a Python RDD, but its parent is Parallel Collection RDD, which is the one that we made it from. The second RDD knows that the first one is its parent. If part of the second RDD is lost, it will recalculate from its nearest surviving ancestor. While RDDs can be created by parallelizing an existing collection, that doesn't help much for big data. If the whole collection fit in memory on one computer, you wouldn't need Spark. The other way to create RDDs is by providing instructions so each executor can pull in part of the dataset themselves. The data needs to be somewhere that's accessible from all of your workers, maybe an HDFS installation or an NFS folder. This is more common in production Spark systems, since loading all the data into your driver program just isn't going to work. This video is going to cover loading data from a text file into Spark. Data in a Spark system lives inside RDDs. If you have already loaded your data into your driver program, you can easily convert it with the parallelize command. Otherwise, you'll need to read the data in from your nodes. One of the simplest ways to do that is with the text file function. The text file function reads a text file from any Hadoop-supported file system URI, including HDFS or a local file system. Remember, because we're sending these instructions out to the executors, we need to make sure that they have access to the file we want them to read. If the file is stored on a file system, make sure it's either available over the network or that the file is available in the same place on each of your worker nodes. Let's see a quick demo where we load a sample file. In this case, it'll be a file full of audio test sentences. Here, we're calling the text file method on the SC object. SC is the Spark context. It's provided by the PySpark REPL. SC is the way that we can interact with our Spark cluster. There we executed it and stored it into the text variable. Let's check. So we have an RDD. Now, let's look at what's inside that RDD with the collect action. And there it is. Note that our RDD is a collection of strings, one per line. This is a really easy way to get data into Spark. There are a couple of optional arguments to text file. The first is MinPartitions, which takes a positive integer. MinPartitions is the minimum number of partitions our data should have. It's important to partition your data because your maximum parallelism will be the number of partitions. If you think about it, this kind of makes sense. The data is split into partitions, and then the partitions are handed out to the executors. If there's only one partition, only one executor will have the data and can operate on it. There's no point in building a giant cluster and then running all the calculations on just one of the computers. I'm going to show you how to use the text file with a MinPartitions of 1. This is probably not what you want to do, but keep in mind, you're only giving it the minimum number of partitions, not the maximum. So although I say the minimum is 1, it could still decide to give me 10. 10 is greater than 1, of course. Because we probably don't want one partition, there's no reason to tell it MinPartitions is 1. This is actually useful if I think, I have 20 machines that are going to be processing this. I want to make sure that at least those 20 machines will have work to do. Then I might use MinPartitions equals 20. Now in this case, it still may not be 20, because if you look, we don't have 20 sentences, so there's no way that it could break this data set up into 20 parts, because it's not going to split sentences. At the same time, I think that these 15 sentences are going to run pretty quickly, so we probably don't need to worry. There are some other factors that will affect how many partitions you end up with. What we're putting in that setting is only the minimum number. A file read in from HDFS will generally have at least one partition for each block in HDFS. Block sizes vary, but are 64 megabytes by default. If you don't specify a minimum partition, then the minimum is the lesser of the spark.default.parallelism setting, or 2. The second optional argument for text file is use_Unicode. This defaults to true. Setting it to false will make the strings UTF-8 instead of Unicode. UTF-8 is faster and more compact. If you're certain your document doesn't have any Unicode characters in it, this is an easy performance improvement. This video is going to talk about actions in Spark. In Spark, RDDs are the nouns, but we need verbs to get something done. There are two main types of verbs to act on RDDs, actions and transformations. Transformations can configure interconnected webs of computation, but they don't actually do anything. Transformations are lazy. It isn't until an action, which wants to create output, asks for the data, that Spark leaps into action. These output-producing functions force evaluation of their input RDD, which forces its parent, all the way back to an input source. Actions are the only way to force Spark to actually do something. Spark can output using any Hadoop output format, or with several other action functions. You can pull values back into the driver program, or even write them out to disk. Let's quickly look at a couple of example actions in Spark. First, we're going to create a numbers RDD. It's going to contain the numbers 0 to 19. You'll notice that we did that using the parallelize method on the SC object. SC is the Spark context that's provided for us with the Python shell. First, we've got collect, which pulls all the data back into the driver program. Excellent. Numbers 0 to 19, just like we expected. We've also got sum, which adds up all the numbers in an RDD. Then there's take, which returns the requested number of elements from the RDD. Let's ask for 3. And finally count, which counts the number of elements in the RDD. Also, maybe we want to save our numbers to disk, in case we ever need to load the numbers 0 through 19. Okay, we've written them out to disk. Spark has many more actions, but hopefully this gives you a feel for some of the things you can do. In general, if a function takes an RDD and returns another RDD, it's probably a transformation. If it takes an RDD and returns something else, then it's probably an action. Nothing happens in Spark until your request output with an action. Then all the transformations are applied. You can read more about Spark's actions in the Spark Programming Guide under the documentation section of the Spark website. This video is about transformations in Spark. All data in Spark lives inside an RDD. An action lets you take an RDD and output the data to something other than Spark, maybe the driver program or a file system. However, input and output are only part of the system. If Spark didn't provide a way to transform the data, it would be nearly useless. Spark's transformations allow us to define computations on our input RDDs. Each transformation operates on at least one existing RDD and returns a new RDD. This new RDD can be the source RDD for another transformation. In this way, you can build up a graph of RDDs, with each remembering what RDD it was computed from and what function is used to do the computing. Because Spark is lazy, nothing happens while you're setting up these transformations. No computation occurs until a Spark action forces evaluation of an RDD, which will force its parent, which forces its parent, and so on, until Spark finds an RDD that is populated by an input source, which stops the recursion. Let's see some Spark transformations in action. First, we'll make the numbers RDD, which is the numbers 0 to 19. Now, let's make a smaller numbers RDD. This one can be maybe 0 to 4. So now we have numbers that's 0 to 19 and small numbers that's 0 to 4. We can verify that with the collect action and also for small numbers. We can look at the ancestry of an RDD with the .toDebug string. Here you can see that we have a parallel collection. It's a Python RDD. Now let's do a transformation that combines these two. Okay, I'm using the union transformation. If we look at the debug string for combined, we should see that it has both numbers and small numbers in its debug string. Let's also check the debug string for small numbers to make sure that it's there. You can see that we have a union RDD. We also have an IPython input 3-894, and then separately, IPython input 4 107b1. That's the two input RDDs get combined into the union RDD. So that gives you a little peek at the computation graph as it's being built up. Spark has a ton of useful transformations. You can read more about Spark's transformations in the Spark Programming Guide under the documentation section of the Spark website. This video is about persisting data in Spark. Spark gives you a lot of control about what data to save and how to save it. The most simple workflow is reading data in, performing a transformation on the data, and writing the results back out to disk. Spark makes this easy, but it isn't the only thing you can do. For example, suppose you want to read data in, do a long, expensive calculation, and then write the results in two different formats. The naive approach would look like this. First, we put in our input. In this case, it's 1,000 numbers. Now, we do an expensive calculation. I will simulate that by raising each of these numbers to the 5th power. This may not be a hugely expensive calculation, but in your mind, think about maybe database lookups or some kind of network hit. Maybe we're scraping web pages over the internet and processing the results. Now, we can use the SaveAsText action to write it to disk. But remember, we wanted to write this out in two different formats, so let's write the second format too. That seems like a reasonable plan. We read our data in, we perform our calculation, we save it as a text file in the first format, we do another transformation to put it into the second format and write it out. Unfortunately, this isn't going to work like you think. When Spark sees that first SaveAsTextFile, it's going to run our expensive calculation and write out the result. Once it finishes, it'll read a little further and see the second SaveAsTextFile. Oops, it didn't realize it needed to save that expensive result. It might still have it in memory, but it might not. Since we spent a lot of effort computing those results, we should tell Spark how important they are. Spark provides a persist method on RDDs that lets you tell Spark to keep the RDD around. Telling Spark to persist an RDD means that any subsequent actions in the same session will not have to go all the way back to input. Once you're done with the RDD, you can call unpersist on it to release it. Alternately, if your job completes or your shell closes, the RDD is going to be discarded anyway. By default, Spark will save the RDD in memory only. You can also pass a custom storage level. You can control several aspects of persistence through the storage level. First, you can control whether the RDD is stored in memory only, on disk only, or memory and spilling to disk when necessary. Memory is going to be much faster, but any memory you spend storing RDDs is going to be taken away from the rest of your workflow. Storing to disk is slow, but you've usually got plenty of it. A memory and disk combination is good when you want to store as much as possible in memory, but are okay with spilling it to disk when you run out. Memory only can run into problems if your data is too large to fit into memory. You can also choose whether to serialize the RDD when storing it. It'll always be serialized when you store it to disk, but you can also serialize it when keeping it in memory. This will convert all of your objects into a couple of large byte arrays, which is more efficient. This is often a good idea when you have a big RDD, since it'll take up significantly less space. Lastly, you can choose the replication level of the persisted data. More replication means you're less likely to lose it if you lose a node. It also means more processes can operate on the data without transferring it if you use it as a source. The storage level class contains several static constants that describe common persistence setups. Let's look at a quick demo. We took our input and we persisted it as memory only. This means that we won't have to recalculate it every time we need it. This probably isn't a big deal since we got that input by parallelizing an in-memory data structure, but think about reading it off of disk. Or, even worse, think about accessing it through some kind of network file system. If you're going to use the input data several times, it probably makes sense to persist it. Here, we can verify that it has been persisted with the isCached property, and see that it's true. Since we're finishing up, let's unpersist it, just to be correct. And you can see that now isCached is false. Anytime you're going to use an RDD more than once, consider persisting it so you don't have to redo calculations. Hello, this video covers Spark's map transformation. Spark's map is the same as the map in the MapReduce programming paradigm. In functional programming, it's common to talk about mapping a function over a collection. Basically, you start with a list. Then you call map on that list, providing a function. At this point, Spark will make a new list from the old list by calling the function on each element of the old list, and then using the return value as an element for the new list. Let's look at a quick example. First, we're going to make an RDD. This is just going to be the numbers 0 through 9. Then, we're going to use the map function, and we're going to follow it off with the collect action. The only thing the collect action is doing is pulling the RDD back into the driver program so that we can inspect it here in the REPL. Here you can see that we used Python's lambda syntax to define an anonymous inline function. That's not the only way we can do it. We could also define it like this. Here we defined a function and then passed that function by name into the map function. Both of those approaches will have the exact same effect. Note that you're passing the function but not calling it. Spark takes care of calling it where needed. Also, you should write it as a pure function. It shouldn't reference variables outside the function. It shouldn't store state outside the function. Because the function is run on many different executors, mutating variables or state outside the function isn't going to do what you expect. If you're trying to calculate a total over all of your input, map isn't the right function. Map is for when you want one output for each input and nothing else. Map is one of the foundational building block functions in distributed data processing. Although Spark offers a lot more flexibility than Hadoop's MapReduce, you'll still end up using map all the time. Anytime you want to create an output for each input, you'll want to reach for map. One special use of map is to create key-value pairs. Key-value pairs are a special type of data in Spark. At a high level, if you want to combine parts of your data, the easiest way is to give all the parts you want to combine the same key, and then use the ReduceByKey function. This can be an expensive action since data has to move between executors, but it's pretty useful. This is the reduce from MapReduce. Map also has one optional argument, preserves partitioning. This is useful for more advanced Spark, where you're keeping track of how the data is partitioned. Read more about data partitioning and how it can speed up your joins on the Spark website. The short story is, once you've partitioned your data a certain way, Spark can remember that and avoid repartitioning later. This optional argument tells Spark that your map function hasn't changed the way the data should be partitioned. In general, you're better off using map values if you are wanting to preserve partitioning instead of using map. Spark's transformations convert one RDD into another RDD. Different transformations do it in different ways. The filter transformation allows you to keep only the elements of the RDD that you want. If you're familiar with SQL, filter is like a where clause. You call filter on an RDD and then provide a function. Spark calls that function on each element of the original RDD. Whenever that function returns a truthy value, Spark pulls that value into the output RDD. Let's look at a quick example. Okay, We've made a numbers RDD that contains the numbers from 0 to 9. Here we've defined a function isEven, and it returns true if the number is even, or false if the number is odd. Here we can use filter to apply the isEven filter, and then use the collect action. All collect is doing is pulling the RDD back into the REPL so that we can see it here. Here you can see what we expect. We get back only the even numbers. Just to verify, let's look at what numbers had originally. Okay, so we went from 0 to 9 to 0 to 8 with only even numbers. The filter transformation isn't complicated, but it is useful. One thing to keep in mind while filtering is that Python may have different ideas about true and false than you do. For instance, you'll notice that earlier, instead of saying true, I said truthy, because there are some values that aren't true that Python still considers to be like true if you use them in a Boolean context. You can check whether Python considers a value truthy with the bool operator. Let's look at some easy ones that you'll probably guess correctly. True is true. Positive numbers are true. Lists are true. False is false, as we would hope. Now for some tricky examples. 0 is false. The rule here is that all numbers other than 0 are true, but 0 is false. The empty string is false in Python. An empty list is false, and an empty dictionary is false. The string false is true because only empty strings are false. So this can get a little bit confusing. If you want to be safe, make sure you're returning booleans from your function. If you're confident you understand Python's truthy and falsy rules, you can make things a little shorter at the expense of readability. You probably don't want to do this, but let's do it anyway. Here, I've defined a function isOdd, which returns x mod 2. Then I apply that as a filter to numbers, and I get back the odd numbers like we expect. But how does that work? Well, this works because x mod 2 will return 1, which is truthy, when the value is odd. X mod 2 is 0, which is falsy, when the value is even. So this is slightly more compact than the isEven function that we defined above, but significantly less readable. If you do this, chances are you'll create problems for yourself and your coworkers in the future. Also, if you filter out a lot of data, you may want to call Coalesce on the resulting RDD. Coalesce reduces the number of partitions for your data, while minimizing network traffic. If you had 1,000 partitions for 10 gigabytes of data, but then you filtered out 99.9% of the data, it probably makes sense to coalesce down to a smaller number of partitions, so that your executors won't spend all their time starting and stopping. For any computing system, there's a certain amount of overhead, and if you have a small amount of data, the overhead of starting and stopping 1,000 executors probably doesn't make sense. The number of partitions also affects the number of output files for many output actions. This video will cover Spark's Flatmap transformation. The Flatmap transformation is useful when you want to map each element of the source RDD to 0, 1, or many elements in the output RDD. That's different from the map transformation. Map takes one input from the source RDD and maps it to one output in the output RDD. So Flatmap is 1 to many, map is 1 to 1. Okay, it works like this. You call Flatmap on the source RDD and provide a function. Spark calls that function on each element of the source RDD. Now, the big difference between Flatmap and map. Spark will flatten the output of the function into the output RDD. This will make more sense with an example. Okay, we're going to load some sentences using the text file function and store them in the text RDD. Let's look at what we've loaded. We'll use the collect action. Okay, that looks great. But my boss wants a count of the total number of words, not sentences, so I'm going to need to split the sentences on spaces. Flatmap is the right tool for this job, because I want to change each input, which is a sentence, into many outputs, which are words. So here, we can use a lambda to define an anonymous inline function. For each input, the return should be that input split on the space character. Because I used Flatmap, instead of getting an output RDD that's each of those sentences broken up into words, I'll get an output RDD that is just the words. It will remove one level of grouping. Here, I'll show you. Just for comparison, let's look at what would have happened if we had used map. Okay, so here, each output then ends up being its own list of words. So the first sentence produced a list of words. The second sentence produces a list of words. So you can see that this might be useful for some things, but if I'm trying to get total counts for the entire document, this isn't going to help me. Okay, remember in our fictional scenario, my boss wanted to get a word count for the document. I can use the count action. 73 words, great. Now obviously, there are other ways I could have counted words, but this one is simple. Whenever you have between 0 and many outputs for each input, you'll want to reach for Flatmap. Note especially that the words from all the sentences are mixed in together. We don't have one list for each sentence. We have one list of the words from all of the sentences. When you Flatmap, nothing tracks what output came from what input. If that's important to you, you should output something in the Flatmap that identifies where it came from, maybe output tuples, where the beginning of the tuple is the source or an ID for the source or something like that. Alternately, you could use map so that each input creates an output list and then you process those in the next step. So remember, if you want each input to produce between 0 and many outputs, you want Flatmap. If each input produces one output, you want map. This video is going to cover Spark's MapPartitions transformation. Spark's map transformation works on elements within an RDD. The MapPartitions transformation operates on partitions of the RDD. A partition is one chunk of the data inside an RDD. MapPartitions can be useful in a couple of cases. First, it lets you aggregate data over an entire partition. Let's look at a quick example. Okay, first we're going to make a text RDD by loading in some sentences. Also, we'll make sure that there are at least 5 partitions. Now, we're going to break those sentences up into words using the Flatmap transformation. Okay, now we've defined a function called CountWords. CountWords takes an iterator, it moves through that iterator, and then it returns an iterator with one item in it, counts. So basically what we do here is for each word in the iterator, we check if that word has already been seen in counts. If it has, we increment the value associated with it. If we haven't seen it before, then we put it into the dictionary and we initialize it with a value of 1. So this should provide us a word count for all of the values in the iterator. If you're not familiar with iterators in Python, basically an iterator is something that you can for loop through. I can for blank in iterator, and whatever I put in that blank as a variable, it will receive all of the values in iterator one at a time. Okay, now we can look over the results from the word counts. Here we can see that for the most part, we don't have any repeated words, but occasionally you'll see something like the gets repeated a couple times within a partition. Also, this highlights that probably we should have lowercased everything, we should probably have dropped periods, commas, things like that. But this is just a quick example. So, this gave us aggregates for each partition. There are ways to do aggregates over your entire dataset, but this might be useful so you can calculate partial aggregates. Maybe you're interested in looking at smaller chunks of the data. You might be able to use this for things like term co-occurrence if you had lots of partitions. So basically, what words often appear together. If you had many partitions, you could look at each partition and say, here are several words that occurred in the same couple sentences. Another use case for the MapPartitions transformation is if you need to do some kind of expensive setup. The most common example would be like a database connection. A database connection can be very expensive to set up compared to just general computing. That isn't too bad if you set up one connection and use it for a long time, perhaps sharing it between different threads. But it'll be a big problem if you have to set it up for every element in the RDD. In this case, using MapPartition would let you make the expensive database connection setup just once per partition instead of once per element. That would be huge savings. The big change would be, inside your function, where we just yielded the counts, at the very end, you would yield each item as you go through the iterator. Here's a quick example of what that would look like. Okay, I'm not going to evaluate this because we get an error, make DB connection is a made-up function. But basically what happens here is we'll still get the iterator. The iterator contains all of the values in that partition of the RDD. So for each ID in the iterator, we would yield db.lookupID. So here we will yield many things, and everything that we yield will end up making up the next RDD, the output RDD. So this iterates through all of the items in the RDD, but only with one database connection per partition. So this could be a significant performance enhancement. This video covers Spark's MapPartitionsWithIndex transformation. MapPartitionsWithIndex is a funny transformation. It doesn't do much more than its simpler cousin, MapPartitions. In fact, the only difference is that it provides the index of the partition along with the partition iterator. Having the index of the partition could be useful for a couple of things. In general, anytime you want to do something externally with your data, you can do MapPartitionsWithIndex to help differentiate the data coming to your external system. For example, say you want to write all of your data out to a sharded database. You could use the partitions index to help decide which shard to write to. Let's look at a quick demo. Okay, this is just pseudocode. The make DB connection function there doesn't exist. But here I think you can get the idea. I have the iterator, and because I'm using MapPartitions, I can do just one database connection for the entire partition, which is going to be a big savings. And then because I'm doing MapPartitionsWithIndex, I also get the partition index. So here I can give the database a hint and say, oh, the shard can be based on the index. This could also be useful if you wanted to do some logging. Maybe you had one partition or a little bit of data that was really bad, and you were struggling to figure out where it was coming from. Maybe you could log which index the partition had, and you could kind of trace it back that way. So most of the time, you'll probably want to use MapPartitions instead of MapPartitionsWithIndex. However, sometimes you need a partition number. You need some way to tell which partition your data is coming from, some way to differentiate between all of the different input streams when you're mapping over your partitions. So when you need to do that, go ahead and use MapPartitionsWithIndex. This video will cover sampling in PySpark. Sometimes the best way to process big data sets quickly is by making them small, then processing them. Sampling is one way to make big data sets smaller. When you sample down from a large data set to a smaller one, each element of the original set has some chance of making it into the smaller set. The field of statistics allows you to make confidence-bounded estimates of your whole dataset, the population in statistics speak, by running calculations on just a sample of that data. But that's beyond the scope of this course. Sampling is most useful when you have lots of data and it's relatively homogeneous. Because not all of the elements of the original RDD will be in the product, you will lose some information. Any calculations on the result are only estimates, but they can often be calculated much faster. This might be especially useful when working from the shell. In an interactive environment like the shell, waiting a minute or two for each answer can be kind of inconvenient. You might sample the main dataset down a lot, run through the process in the shell to make sure things work as expected, and then run the process on all the data as a non-interactive Spark job. Let's see how this works. Here we have a relatively large data RDD. You can see that it has 10,000 elements. Here, you can see that by using the sample transformation, I cut the data set down to 1/10 of its previous size, roughly. That first false means we're sampling without replacement. Sampling without replacement means you can pull an item from the source set more than once. Without replacement means you'll never get a double. One way I've heard it explained is to think of a bag full of balls. With replacement means that you put the ball back in the bag before you draw one out again. Without replacement means that you just keep pulling them out. The second argument is the fraction, or how big we want the result set to be. If you are sampling without replacement, the fraction should be between 0 and 1 exclusive. Sampling with a fraction of 0 would be throwing away all your data, so there's really no reason to do that. Sampling with a fraction of 1 wouldn't be sampling at all. Sampling with replacement is often used for statistical bootstrapping methods. There is also an optional seed argument to the sample function, which is important for repeatable runs. Sampling happens randomly, so if you want others to repeat your process, you need to provide the seed for your random number generator. Sharing the seed means your random process will turn out the same every time. This video will cover the union transformation in Spark. The union transformation is one way to combine RDDs in Spark. Union adds the contents of the two RDDs together. It doesn't do anything complicated or fancy like removing duplicates or sorting. It just adds them together. Let's look at a quick example. Here you can see that our first RDD is the numbers 0 through 4. And here you can see that our second RDD are the numbers 5 through 9. And here you can see that when we take the first RDD and union it with the second RDD, and then collect the results so that we can see them, it's the numbers 0 through 9. So all union does is add the second RDD to the first RDD and return a new RDD that's the union of the first two. I've used union when I have data coming from multiple places and I wanted to combine it. Maybe you're loading some data from a database, but you also have data coming in from the file system. With union, you could pull the data in from several places and stick it all together for your processing pipeline to handle. This video will cover Spark's intersection transformation. The intersection transformation is a way to see what elements exist in both of your input RDDs. Let's look at an example. Here, the first RDD is the numbers 1 through 5 with 1 repeated twice. And the second RDD are the numbers 1, 1, 4, and 6. So here, starting with the first RDD, we use the intersection transformation with the second RDD to create an RDD that was the intersection of the first two, and then we collected it to bring it back into the REPL. Here we can see that 1 and 4 are the elements present in both RDDs. Note that there aren't duplicates output, so we don't see multiple 1s, even though both RDDs had more than one 1. Internally, Spark uses a reduce to check the intersection. Without going into too much detail, a reduce has different performance characteristics than some other transformations. Data has to travel from the executor that read it in to a different executor, which is determined by the partitioner. Because of all this data travel, it can be a lot slower for large datasets. All of the communication between executors can overwhelm your cluster's networking. However, don't avoid this just because it might be slow. Try it out. It'll probably work. But if your workflow is slow and you aren't sure why, transformations that cause reduces are a likely candidate. This video covers PySpark's distinct transformation. The distinct transformation drops duplicates from an RDD. This is useful in a lot of situations. Let's look at one example. So here we made an RDD using the Cartesian transformation. It took the first RDD, which was A and B, and the second RDD, which was the numbers 0 to 99, and did a Cartesian product of them. That just means it made every possible combination. So we have an A with 0 to 99 and a B with 0 to 99. Now, let's say that this was the list we started with, and we wanted to find out what are all the values in the first spot. Because we made this list, we know it's A and B, but let's pretend we don't know that. So how could we figure that out? Okay, so we can use the map transformation with a lambda that pulls the first item out of its input. When we collect that, we see that we get a pretty large list of A's and B's. But let's say that was a really large list, and we weren't comfortable just scanning through all of it. You know, there might be a C somewhere in there, or a D. Well, let's use distinct so that we only see unique values. There. Now we've got a list of just the distinct values. If there had been a C or a D in there, we could see it easily in this list of 2 or 3 or 4 items. That's a lot better than scanning through 200 items, or 2,000, or 2 million, however large your dataset is. You should also know that distinct takes an optional argument, MapPartitions, which sets the amount of output partitions. The higher you set this, the more parallelism you get in the distincting operation. Note that distinct uses a reduce underneath, so it's going to be slower than non-reduced transformations with big data or slow cluster networks. This video is going to cover PySpark's Cartesian transformation. The Cartesian transformation is a way to join two RDDs together. The name comes from the set theory operation Cartesian product. In set theory, we would say that the Cartesian product of two sets, A and B, is a set that contains all pairs x and y, such that x is a member of set A and y is a member of set B. Cartesian products are useful when you want an all pairs comparison. For example, if there are 5 kinds of ice cream and 7 types of cookie, then the Cartesian product of ice cream flavors and cookies represents all possible ice cream cookie combinations. We can calculate Cartesian products in Python with nested for loops in a list comprehension. So here I've created 5 types of ice cream and 7 types of cookie. Now we can do a Cartesian product with the nested list comprehension. So here you see that A represents all of the ice creams and B represents all the cookies. And here we have every possible combination of ice cream and cookie. Now let's do the same thing but in Spark. Okay, we've made an RDD that represents our ice cream flavors. There are still 5. And now we've made a cookies RDD that has 7 flavors. And here you can see that we did a Cartesian product and ended up with the same thing as the nested for loop in Python. Doing it in Spark lets it happen on the cluster, so for large data sets, you won't be able to do it at the REPL, you'll have to do it over Spark. Now, a word of warning. The size of the resulting Cartesian product is equal to the product of the input sizes. For example, if you have 100 items in the first RDD and 200 in the second, the Cartesian product will have 20,000 items. Now, 20,000 items isn't a problem on most clusters, but we're talking about big data. If one of your input RDDs has millions of rows, and the other has billions of rows, maybe some time series data, well, you've got a problem. In general, you can't do Cartesian products between 2 large sets. If you need to join 2 big sets, it makes sense to think of ways to join smaller parts of the data. Spark provides some other tools for joining large data sets, including join, full outer join, left outer join, and right outer join. A lot of those will sound familiar to you if you come from a SQL background. Using one of those is probably the only way you'll be able to join large data sets. Also, you could broadcast a small data set out to the large data set using broadcast variables, and then use a map transformation to apply the small data set to each item of the larger data set. For large data sets that need to be joined, consider the join transformations or using a broadcast variable. If your input data sets are small enough, the Cartesian transformation can be a quick and easy way to compute all possible pairs. This video covers the pipe transformation in PySpark. The pipe transformation refers to the Unix process communication tool of the same name. Pipe, in Spark, takes each partition of data and pipes it through the command line tool you specify. The command receives all the data from the partition, 1 item per line. Then, the output from the command is the resulting RDD, each line becoming 1 item in your new RDD. This is really useful when you have already developed a command line application to do the processing you want, but now you need to parallelize it. Your command line tool can be in any language you want. While many languages don't have a Spark interface, any language that can read from standard in and write to standard out can be used with pipe. You can even use the classic Unix tools like grep or sed. In particular, you could use grep as a quick and easy filter command. This way, all the time you spent learning grep flags and regex syntax can continue to pay off. Let's look at a quick example. Here we made an RDD with the numbers 0 through 10. And here we used grep to filter it to keep only the things that had the digit 1. Now remember, grep operates on strings and pipe passes all of your data as strings. So even though we had integers, those got coerced into strings and then grep operated on them as strings. Although the pipe tool doesn't do much on its own, it opens up the entire world as potential Spark tools. Any command line tool that can operate on a partition's worth of data and return useful information is usable. Your company's expensive, well-tested, magic codebase can be integrated into Spark as long as it can read from standard in and write to standard out. It's hard to overstate how useful the pipe transformation can be. Also, because the input and output happens at the partition level, you don't have to worry so much about command line tool overhead. Many dynamic languages, like Python, can be kind of slow to start up on the command line. However, because Spark only starts the program once per partition, your slow startup is amortized over the number of elements in the partition, which ought to be large. Overall, pipe can operate as a map, a filter, a flat map, a sort, all kinds of things. Let's look at some quick examples. So here I've made our test RDD. It's 3 strings, B, B, C, 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 and A. Here I used the pipe command along with the Unix translate command to capitalize everything in our source RDD. Here I used pipe as a filter. I used grep again to pick out everything that has an A in it, which was only our last element, A. Here, I used pipe as a flat map. I used translate again to find every instance of a comma and replace it with a new line. Now because pipe just reads from standard out, every time there was one line on standard in, there could be multiple lines on standard out. That's what happened here. The string with the A in it only generated one output, but the string with the B's generated 2 lines of output, and here they are in our output. You can see that pipe gives you the freedom to apply any other tool to your data. This video covered Spark's pipe transformation. This video covers Spark's Coalesce transformation. To understand the Coalesce transformation, you have to understand a little about how Spark stores your data. Since Spark was made to handle large datasets, it doesn't try to store it all in one place. Instead, it stores the data in chunks, called partitions, all over your cluster. Many input functions allow you to hint how many partitions you want for your data. The Coalesce function allows you to reduce the number of partitions in an efficient way by combining partitions that are already on the same executors. Let's look at a quick demo. Here, we made an RDD with 100 partitions. And now we made a second RDD out of the first one that only has 10 partitions. So we reduced the number of partitions to 10 with a minimum of data movement between executors. There's usually still going to be some network traffic, but this is more efficient than a complete repartition. So, although I've told you how to switch the number of partitions, you might be wondering, well, when do I need to switch? How do I know what I should switch to? Choosing the correct number of partitions is a balance between 2 motivating factors. The number of partitions is the upper limit for parallelism. You can't have 5 processors working on 3 partitions. The Spark docs recommend 2 to 4 partitions per CPU in your cluster. However, you can also have too many partitions. If you have a dataset with 1,000 values, it probably doesn't make sense to have 1,000 partitions. Every time you start a computation, there'll be 1,000 sets of task overhead. The task overhead will dwarf the actual computation of the element. The number of partitions also determines the number of output files for many of the output actions. Remember, in general, you want 2 to 4 partitions per CPU in your cluster. Then, try cutting the number in half and see if your job gets faster. Double it, see if it gets faster. Most tuning starts with an educated guess and ends with a parameter sweep to see what particular settings work for your job. This video covers the repartition transformation in PySpark. So let's talk about partitioning so that we can understand repartitioning. Spark places parts of your RDD on each of the executors in your cluster. RDD stands for Resilient Distributed Dataset, so we've got to distribute it. Spark uses a partitioner to decide which data should end up on each node. A good partitioner should put the same amount of data on each node. Loading one node extra heavily and another one lightly will cause performance issues. The one with more data will take longer to complete. This is often called a long-tail performance issue. It's a big pain because all of the other executors end up waiting for the slowest one to complete. Each stage is only as fast as its slowest task, so spreading the data evenly is important. Some versions of Spark allow you to specify your own partitioner to get fine-grained control over which data goes to which executor. PySpark doesn't let you do this with the repartition command, but it does let you do it with the repartition and sort within partitions command. So if you need to specify a custom partitioner, check that out. The repartition command does let you set the target number of partitions. This is similar to Coalesce, but we can also grow the number of partitions. Here's a quick example. Okay, so this is how I would make an RDD with one partition, where I use the num slices equals 1, and then I can use the repartition command to create a new RDD that has 100 partitions. Repartitioning your data means sending it from its current location to its new host executor. That can mean a lot of network traffic for a large dataset. If you're reducing the number of partitions, you should consider using Coalesce instead, since it can often accomplish the same effect without as much network traffic. It tries to combine partitions that already inhabit the same node to reduce data shuffling. Picking the right number of partitions can be tricky. Too many, and you waste time because the task startup and bookkeeping dominate the actual work. Too few, and you won't be able to use all your cores. The Spark docs recommend 2 to 4 partitions for each CPU in your cluster. That makes sure they'll all be able to work. That number might be too high for an RDD with a small number of elements. Start with a recommendation, but play around with reducing the number. This video is going to cover the repartition and sort within partitions command from PySpark. Repartition and sort within partitions is just the right tool for a pretty rare job. If you need to repartition and then sort data within the partitions, then repartition and sort within partitions is the right tool for you. Repartitioning means changing the number of pieces your RDD is broken into. Repartitioning moves data around the cluster, either to spread it out, or to consolidate it, or to change the way that you're chunking it. Because of the way Spark does the repartitioning, it isn't much extra work to sort the data right then. If instead you did a normal repartitioning and then a sort later on, it would be less efficient. One other difference between repartition and sort within partitions is that you need to provide it with pairs. It operates on key value pairs, and the repartitioning happens based on the keys. First, let's make a sample dataset. So here you can see the output, and there's a couple of interesting things. First, I use the glom command, and what that does is take all of the elements within a partition and put them into a list, and then return an RDD of those lists. So here you can see that at the furthest out we have a list, and then within that there are 2 elements. First is a list with 1 element, 2, 3, and second is a list with 3 elements, 1, 1, 1, 2, 3, 3. So those 2 lists represent the 2 partitions that I asked it to make. Then you can also see that within those partitions, things are sorted. Because we partitioned by the first value in each of the key value pairs, we're really happy to see that 1, 1 and 1, 2 ended up in the same partition. That's what we asked for. Also, you can see that 1, 1 comes before 1, 2, and they both come before 3, 3. That's also what we would expect with a normal Python sort. Repartition and sort within partitions has a couple of interesting optional parameters. You can provide a partition function, which allows you to tell Python how to assign items to partitions. This is pretty powerful. Okay, so here I specified my own custom partition function. I said, for each key that comes in, is it equal to 1? And here you can see in the output that we have 2 partitions. The first has 2, 3 and 3, 3. Neither of them are equal to 1. This must be my false partition. And then 1, 1 and 1, 2. Those are equal to 1. So here I was able to create 2 different partitions of my data based on an arbitrary rule. Later on, if we were going to do a MapPartitions to load these into a database or something like that, this is a way that I could kind of pre-shard my data so that it went to the right database shard. The next optional parameter is ascending, which controls the sort order. You can also provide the keyfunc function. This tells Spark how to get the value for each element when sorting. You could use this if you wanted to sort dictionaries by a certain attribute or tuples by the second item in the tuple only, something like that. When you want to partition and sort, use RepartitionAndSortWithinPartitions. Also, if you want to be able to specify the partition function, you'll need to use this because the normal repartition function in PySpark doesn't allow you to pass in a partition function. To me, it seems like this will probably change in future versions of Spark. There's not a great reason that repartition and SortWithinPartitions can do custom partition functions and the vanilla repartition function can't, but that's how it is for right now. This video will cover the reduce action in PySpark. Reduce is one of the two most famous distributed programming functions, alongside its partner map. MapReduce is the dominant distributed programming paradigm, made famous by Google in its MapReduce paper, and open sourced by Yahoo as Hadoop. Reduce provides a way to calculate aggregates over many inputs. To use reduce to calculate an aggregate, you need to provide it with an associative, commutative function of 2 arguments. Spark will calculate the summary by applying the reduce function to pairs of input elements, and then applying the function to the results of those pairs again and again until there is only one output left. You can think of reduce as a giant tournament bracket for your data, except that the winner of each game is often some combination of the 2 teams. First, let's explore what it means to say that the function has to be associative and commutative. Associative means that the order of application doesn't matter. For example, addition is associative. However, subtraction is not associative. Associative means that the order of application doesn't matter again. So you can see that here in our addition example, if 1 and 2 go first, or if 2 and 3 go first, doesn't matter. However, in subtraction, it does matter. Since reduce doesn't guarantee which of these will happen, you have to have a function that behaves the same in both cases. So you can reduce with plus to find a sum. You cannot reduce with minus. You would get different results every time. The reduce function that you provide also has to be commutative. That means that the order of arguments to the function doesn't matter. Again, addition is commutative. 1 plus 2 is the same as 2 plus 1. And again, subtraction is not commutative. Here you can see 1 minus 2 is clearly not the same as 2 minus 1. So, the reason the function you provide to reduce needs to be both commutative and associative is because there are no guarantees about the order in which elements will be fed into the reduce. Also, the reduce tournament will proceed in parallel, since order doesn't matter. Each executor can reduce its partition down to one value. Then that value can be sent to other reducers, and all of their values can be combined. This saves a lot of network traffic, since you're only sending the final winning value from each partition. Let's look at an example that looks a lot like a tournament. So here we can see the contents of each of the partitions because we use the glom function. So our partitions are 0, 1, 2, 3, 4, 5, and 6, 7, 8, 9. Now let's use the max function to find the highest value in the dataset. Here, the winning value is 9. Internally, reduce probably did 0, 1, and 2, found that the max was 2. A separate executor could work on the next partition, compare 3, 4, and 5, find that 5 was the best. A third executor could work on 6, 7, 8, 9, find out that 9 was the best. Then 2, 5, and 9 could be compared, and 9 could be the best. Now you can see that because we're allowing each of them to operate independently, we can get 3 times the parallelism here, or 3 times the throughput through parallelism. We can also use a reduce function that incorporates both arguments instead of just picking one of them. So here, we just added each of them together all the way through. Reduce is one of the primary tools for generating aggregates over your data. If you want to generate aggregates for some subset of your data, similar to a group by in SQL, then check out the ReduceByKey function. It lets you specify which elements belong to which group by the key, the first element in the pair, and then generate aggregates for each individually over the second attribute in the pair. This video will cover the collect action in PySpark. If you've read or listened to any Spark tutorials, you've already seen collect. Collect allows you to pull all the data in an RDD back into the driver program as a list. Here's a quick example. So here we made an RDD with sc.parallelize, and then we used collect to pull it back into the driver program, which happens to be this PySpark REPL. Now be careful with this. If you just read 50 petabytes of data into your mega cluster, you don't want to collect that back into your driver. It's not going to work. It'll probably hang for a while and eventually die. If you're just playing around with some small data sets, like the demos I'm showing you, you should be fine. If you're doing some exploratory data analysis, collect can be really useful to let you peek into your data. You might consider using sample to decrease the size of your data, then using collect to bring it back into your REPL. So here, I made a huge RDD that was way too big to pull back into my driver. Well, actually, 100,000 probably would have been okay, but let's pretend. Now, I used sample to sample my huge RDD way down. In this case, I probably oversampled a little bit. I only got 2 elements back. But you get the idea. Up that fraction a little bit so you get something that's big enough to be interesting, but small enough to fit easily on your computer. That way, I can check out a random sample. Because I provided seed to the sample argument, it's going to be consistent. Every time I do it, I'll see the same thing back. You could also do a filter or some other kind of transformation that greatly decreases the size of my data set so that it wouldn't overwhelm my computer. Well, that's all there is to it. Collect is really useful, but it's not very complicated. This video will cover the count action in PySpark. The most basic form of count tells you how many items are present in your RDD. Here's a quick example. The basic count function is really useful, but there isn't a lot more to say about it. It doesn't have any optional parameters or things like that. However, it has a couple of interesting cousins. The first one is countApprox. CountApprox allows you to provide a timeout and a confidence. This allows you to get an approximate count, which can be faster if you don't care exactly how many items you have. If you're doing some kind of flow reporting, odds are no one cares whether you had 10 billion and 1 events instead of 10 billion. There's no reason to wait to be absolutely sure. Here's how you would use countApprox to get an approximate count for the numbers RDD. Okay, well that seemed like it returned faster to me, but for numbers this small, there's probably not going to be a big difference. In practice, you'll probably want to play around with your confidence and timeout to make sure you aren't generating complete junk, but you're generating it fast enough to be worthwhile. The last interesting count action is countApproxDistinct. CountApproxDistinct does an approximate count of the number of distinct elements in your RDD. This is different than the other count functions, because it's counting distinct elements, not all elements. So if your RDD had number 1 5 times, countApproxDistinct would only return 1, because there was 1 element, even though there were 5 of them. Under the covers, Spark is using the very cool hyperloglog algorithm to do cardinality estimates. To grossly oversimplify, hyperloglog works by hashing your data into buckets, then seeing what the smallest value in the bucket is, then roughly estimating how many elements there probably are in the bucket if it has an element of that size. Hyperloglog then takes a harmonic mean of all of its estimates to produce the final estimate. You can set the relative SD parameter to control the accuracy. Smaller values are more accurate, but use larger and slower data structures. The default value is 0.05. Here's a quick example of how you'd use countApproxDistinct. Counting distinct elements in a large dataset is a challenging task. CountApproxDistinct makes it easy. Here you can see it was an approximate estimate. We were off by right around 3% for our count. So we could change the relative SD parameter to be more accurate at the cost of being slower, but this is a pretty good estimate. If you've ever done cardinality counting yourself, the easiest alternative is to just keep a set of all the things that you've seen, but that's going to take up a huge amount of memory. CountApproxDistinct, with the hyperloglog underneath, is much more efficient. This video will cover the first action in PySpark. And by that I mean the action named first, not the first one. So, sometimes you just need one item from your RDD to play with in the REPL. Or maybe you've combined and reduced your RDD down to one item and want to pull it back into the driver program. In either case, you can use first to pull the first item from your RDD. Here's a quick demo. First is pretty simple. It doesn't have any optional parameters. It does respect any sorting that you've done. So here's a quick demo of that. So here you can see that the RDD was 3, 2, 1, but then we sorted it. We used just the identity key, so sort each item by its natural sort order. And then we took the first thing. So because 1 would have been first in the natural sort order, that's what first came out with. Here you can see that you can't use first or most other actions on an empty RDD. So there you have it. First isn't complicated, but tools don't have to be complicated to be useful. This video will cover the take action in PySpark. The take action returns to the driver program any number of elements from the RDD. Take is the general purpose return to driver command. Here you can see that taking 1 is almost exactly the same as using the first action, although take returns it as a list and first just returns the element. Here, when I take as many numbers as there are in my collection, that's the same as using collect. However, if you just want one item, use first. If you want all of the items, use collect. Using the specialized function instead of the more general take means that it can be better optimized underneath. Take looks at one partition and then estimates how many partitions will be needed to provide the number of elements you requested. Then returns all of the elements for which you asked to the driver. This video will cover the TakeSample action in PySpark. TakeSample allows you to pull a random sample of elements from an RDD into your driver program. When you sample, you need to provide the target sample size as well as whether you want replacement while sampling. Sampling without replacement means that you can only select a given element once. Sampling with replacement means each element has an equal chance of being picked for each element in the output RDD. That means that although it's quite unlikely, theoretically you could have the same element pulled for every item in your output. So if your input were the numbers 1 and 2, and you were sampling with replacement, you could generate an output RDD of 10 ones. It's unlikely, but it could happen. You can also provide a random seed when sampling. This is important because it allows others to replicate your findings by making the same random selections as you. This is known as repeatable research. Let's look at some quick examples to see how TakeSample works in practice. Here, we used TakeSample on our original numbers RDD. The original RDD had the numbers 0 to 9. We sampled without replacement, and we're just looking for one item. You can see num equals 1. So the number that was chosen at random was 8. Because we provided a seed, 8 will always be chosen, even if we ran this again. And here you see, we got 8 again. Now let's try it, but let's change the seed. Here you see, different seed, different result. So this might surprise you. You can see that I take sample on numbers, and I asked for it to give me 100,000 items. But because I said with replacement false, it never puts any of the numbers back. So after it pulled all 10 elements out of the RDD, there was nothing left to sample, so it just returned what it had. It gave me all 10 of the numbers that were in my original RDD, probably in a different order, but still only 10. I asked for 100,000, but I got 10. Now, look at what happens if we do that with replacement equals true. Okay, so this time, there are 100,000 items in the output. Even though our input RDD, numbers, only has 10 elements, because we replaced them after sampling each element out, it was able to pull 100,000 elements out of just 10. When sampling with replacement, you can take as many samples as you want, since you can pick the same item more than once. This video will cover the TakeOrdered action in PySpark. TakeOrdered is a special form of the take action that you've probably already seen. Here's a quick demo just to remind you. So, take just takes the first 10 numbers from the RDD in the same order as it was given them. If you take ordered, it's similar to sorting the entire RDD and then taking. Here's an example. Here you can see that our output is sorted. In this case, TakeOrdered ended up sorting our entire RDD, but that's because it only had 10 items to start with. If you have many items and you take a much smaller number, then you don't have to sort the entire dataset. One way that you could do it more efficiently would be to reduce over each partition, keeping the first n elements by sort. Then combine the resulting lists in a reduce, then do a final combine in the driver. At each point, you'd only need to keep the top n items, which could be really fast if n is small. Because Spark knows that you're doing a take ordered, it can do that behind the scenes so that you don't have to do all that work. But it's only really fast if n is small. That brings us to our next point. Don't take ordered when n is almost the same size as your dataset. If you want to sort your entire dataset, just sort it. Don't take ordered it. Take ordered works best when n is small. Take ordered also lets you provide the key function. If you're sorting an object and want to sort along one attribute, or if you want to reverse the sort order, you can provide a key function to do that. It'd look like this. Here you can see that our key function just reverses the sign on our numbers. So 1 becomes -1, 2 becomes -2. Note that this isn't the same as mapping the negative sign across all of our numbers, because the output are all still positive numbers. The key function doesn't change the output, it just changes the value according to the sorting. This video will cover the SaveAsTextFile action in PySpark. The SaveAsTextFile action is a great way to get data out of your Spark workflow and onto a disk. SaveAsTextFile calls toString on each element of the RDD and writes the results out, one per line. Also, you'll get one file per partition of your dataset. You can save to a directory on the local file system or into any Hadoop-supported file system, such as HDFS. It's pretty common to repartition before using SaveAsTextFile to control the number of output files. Having a huge number of tiny files will waste space in HDFS and slow down subsequent jobs. Let's look at a quick example. Okay, so here, first we made an RDD called numbers. That RDD consists of the numbers 0 to 999 inclusive, and we provided the numSlices argument of 5, which meant that we made it 5 partitions. Now we used SaveAsTextFile on that RDD and gave it the name OurTestNumbers. So what we expect to see is a directory called OurTestNumbers that has within it 5 files, and each of those files should have some of the numbers. So let's check it out. Here you can see that we did have a folder named OurTestNumbers, and within it we have the 5 files we expected, plus another one, the _success. _success is something that most Hadoop output formats put in there automatically. That means that it's done writing. If you look at an output directory and it doesn't have that _success, it means that Hadoop isn't sure that it's done writing there yet, so you should probably wait. All that means is you can safely ignore it. And here you can see that a bunch of the numbers from our RDD are present in part 000. SaveAsTextFile also accepts an optional compression codec class argument, which defaults to none. This is where you can tell Spark you want a special output format. A commonly used one is Hadoop's gzip codec. Okay, so here we saved our RDD again, but this time we specified the compression codec class. This means that the output is gzipped. If you haven't dealt with compression before, basically it just makes the text file smaller by looking for repeated patterns and substituting it with something that's smaller that represents the larger repeated chunk. What you'll notice is that it takes a little bit longer to read and write, but it takes up a lot less space. If you're processing a lot of text data and saving it to disk, you definitely want to look into compression. Note that we used a string to specify the class we wanted. Hadoop has several compression codecs with different trade-offs between speed, compression ratio, and portability. When outputting data with SaveAsTextFile, make sure that the toString method is useful. Without a little bit of thought, you could end up with a giant file full of human-readable entries that are no longer machine parsable. It's a lot easier to write a good toString method up front than to write a regex parser afterward to fix your mistake. As a matter of fact, if your data is going to be read back in, you should investigate SaveAsPickleFile. That's a different function that'll allow you to save and reload objects using Python's pickle function. Alternately, you can use something like thrift to write your data out and read it in quickly and efficiently. Finally, one neat trick. Writing data to HDFS can be a little tricky from the command line. One easy way to write some data into HDFS is to parallelize the data into an RDD with one partition, and then SaveAsTextFile that data into HDFS. I use this at work to write run reports or metadata alongside the processing results. This video will cover the CountByKey action in PySpark. The CountByKey action works on key-value pair RDDs. Anytime you see something by key, you can assume that it's going to want key-value pairs as input. Creating a key-value pair RDD in PySpark is simple. You just parallelize a series of tuples. The first value in each tuple will be considered the key. The second value will be considered the value. It'll look something like this. That gives us an RDD with 3 pairs. Each element has a key and a value. Key-value pair RDDs are kind of like Python dicts in that each element has a key and a value. However, unlike a dict, there can be, and often are, many elements with the same key. If you look at our example, there's one element with the key A and 2 elements with the key B. That would be impossible in a Python dict because the second one would have overwritten the first one. Also, there's no random access quick lookups like in a dict. So we have this pairs RDD, but there's no quick way to say, hey, what's the value for A? That kind of makes sense because if I said, hey, what's the value for B? The answer is, well, I guess the value is 2 or maybe 3. So this is a pair RDD, but it is not any kind of one-to-one mapping. Okay, once we have a key-value pair RDD, we can use CountByKey to see how many times we see each key. As you can see, the results are returned to the driver program as a Python dict. One simple problem that this could be really useful for is if you had a data set where the key was the employee ID and the value was the case report. By using CountByKey, you could see how many cases each employee had been involved in. This action completely ignores the values. So here you can see that we had the key A once and the key B twice. But it doesn't know anything about the fact that A had the value 1, B had the value 2, and B had the value 3. The values are completely ignored. If that doesn't work for you, you could do some kind of map or filter before you did this count. Maybe if you only wanted to count where the value was above 1, then you could do a filter before your CountByKey. CountByKey is pretty simple. It doesn't have any special options or arguments. This video will cover the ForEach action in PySpark. Distributed functional programming is a lot of fun, but sometimes you need side effects along with your calculations. That might be incrementing values in an accumulator, pushing data out to a web service, or dropping data into a queue for further processing later. When you need to take an action for each element of your RDD, you can use the ForEach action. For example, let's look at putting numbers into a queue for later processing. So this function takes an argument and adds it to a queue that it maintains internally, and then it returns the queue so that we can see what it looks like. So here you can see that I added 3 and then 4, so now I have a queue internally of 3 and 4. If you're wondering how this works, it's because when I presented the default argument for queue and gave it the empty list there, it doesn't recreate that every time. That's just one list that gets carried through. So this might not be the most robust way, but since I'm just doing it for a demo, I'm not worried about it. Now let's make an RDD full of other numbers to put into the queue. So here, I made an RDD called numbers that has 100 numbers in it, from 0 to 99. Then I used ForEach to call add to queue with each of those numbers. Now we can see what's inside add to queue by adding one more number to the queue, and it'll spit out its current value. Whoa, that's unexpected. We just have 3, 4, and 5. Where's 0 through 99? Well, here's the problem. We have external executors. The queue that we see is just from the driver program. That add to queue function was also executed in the executors that had their own code. They had their own variables. Each of the executors got a copy of the add to queue function. However, once they finished adding to it, it got discarded. Spark doesn't, by default, push changes to variables back into the driver program. That makes sense when you think about it, because Spark doesn't know how to combine the queue it'd get from each executor. If you want to combine data from executors, you can either use a reduce or an accumulator. If we had created an accumulator for our queue, we could have taught Spark how to combine the values from all the different executors and then gotten an answer back. Pushing data into an accumulator is one of the primary uses for the ForEach function. ForEach is also useful if you're pushing to an actual external service. If our queue had been a real Kafka queue instead of this half-baked local variable, it would have worked just fine. The problem is that lots of people forget the difference between the driver program and the executor environment. Spark makes it easy to move between them, but you should always remember where the code you're writing will run. So, in summary, ForEach allows you to execute some code for each element in your RDD. You can use it to push data into an external service, or to make sure everything ends up in an accumulator. This video will cover the GroupByKey transformation in PySpark. GroupByKey is one of the many by-key transformations and actions in PySpark. It allows you to operate on key-value pair RDDs according to their key. In this case, it puts all of the values that have the same key into one iterable. Let's look at a quick example. So here we've made a pair RDD that has the pairs A1, A2, B3, and C4. We also specified it num slices equals 4, which means that this is in 4 partitions. Now we can use GroupByKey and collect. Okay, so this is a little hard to read, but you can see on the left that we have A, C, and B. Then on the right, we have these result iterables. So each of those result iterables you can iterate through to see all of the results inside it. So let's do the first one. So what we have here calculates it again, then it uses the 0th index, so that gives us the pair with the A in it. Then we index to 1, which gives us the value, this result iterable. Now, let's iterate through it with a list comprehension. And here you see that the values we had were 1 and 2. If you look at the original, you can see that we had A1 and A2. So it did group everything that had the A key into one iterable. This is a great way to get a list of values for each key. However, if you're going to do some kind of calculation on that list, you might be better off checking out ReduceByKey or AggregateByKey. Spark can do the reduction or aggregation as part of the transformation, which allows it to be more efficient. Also, the default parallelism is the number of partitions in the input. In our demo, that was 4. GroupByKey uses a reduce under the hood, so you might experience some degraded performance as compared to a map-only transformation. Data has to move from the executor that read it to the one that's collecting the values for that key. All of that data movement can slow things down, but sometimes you need to do it. Just be aware that working to reduce the number of reduces can have a drastic impact on your pipeline performance. This video will cover the ReduceByKey transformation in PySpark. ReduceByKey is a great tool for calculating aggregates over your dataset. If you wanted to calculate a single aggregate over your entire dataset, you would use the reduce function. However, you often want to do aggregates for some subset of your dataset. Maybe you want to calculate total users per state, or total hits by country. In this case, doing it within a normal reduce would be a little bit tricky. Instead, you can convert your input data into pairs, where the key is the value you want to aggregate by. Then, you can use ReduceByKey with the proper reducing function to do the work. Let's look at a quick demo. So, pretend this is a web log for your server, and you see that you have 2 hits from Texas, 1 from California, another from Texas, and another from California. We probably don't need Spark to analyze 5 hits, but it could be informative. Now that we have these, we want to know how many hits did we have from each of the states. Okay, so the way that we got these counts was we started with the state's RDD. Then we mapped a lambda function that turned each of those entries into a pair. So Texas became Texas, 1. Then we ReduceByKeyed across the entire thing using the addition operator. Then we collected the results. So every time we saw 2 things with matching keys, we added them together. Since there were 3 1s, when all of the Texas numbers got added together, we ended up with 3. Since there were 2 Californias, when we added them together, we ended up with 2. You would use a very similar algorithm to do word counts, which is something that comes up kind of a lot. The trickiest part of ReduceByKey is setting up the reduce function. The function you pass has to be commutative and associative. Because the framework can't guarantee which values will be seen first, your function needs to give the same answer no matter what order it sees its input. Addition and multiplication both have those qualities. 1 plus 2 is the same as 2 plus 1. Also, 1 plus 2 plus 3 is the same as 1 plus the quantity 2 plus 3. The same for multiplication. However, subtraction and division don't have those properties. So 1 minus 2 minus 3 is not the same as 1 minus the quantity 2 minus 3. In our case, we just wanted to add stuff up, so we don't have a problem. If you're struggling to think of a function that can do all of that at the same time, you might have better luck with the AggregateByKey function. It allows you to provide a couple of functions, so you can prepare the values in one function and then combine them in another. Also, if your reduce task is just putting all of the elements into a list, you should use the GroupByKey transformation instead. It does exactly that. If there's ever a function that does exactly what you want, you should prefer it because under the hood, Spark can optimize it. It might get faster over time without you doing anything. Remember, ReduceByKey allows you to calculate aggregates over your data, grouped by whatever value you want. This video will cover the AggregateByKey transformation in PySpark. AggregateByKey is similar to ReduceByKey, but it gives you a lot more flexibility. Unfortunately, that flexibility comes at the cost of complexity. AggregateByKey takes 3 arguments to allow you to describe the aggregation you want to do. This is a little confusing, so let's look at an example while we talk through it. In this example, we want to build a set of all the values we saw for each key. The first argument you provide to AggregateByKey is the 0 value. This is the value that the second argument starts with. In our case, we want to start with an empty set, since we're building up sets. The second argument is responsible for adding values from the RDD to your 0 value. In this case, it needs to know how to add an item to a set. The third argument combines the results from different partitions. In this case, that means it'll need to know how to combine 2 different sets. Now, you might have noticed that in our seek op function, we're modifying the first argument. They pass in an x and a y, and then we modify x and return it. In general, that's bad programming. If you modify your arguments, you can really confuse some people. However, Spark explicitly allows you to modify the first argument. That prevents you from having to reallocate all the memory for your collection every time you add a value to it. Now let's make a test dataset. Okay, so this is probably a little confusing. So let's collect it just so you can see what it looks like. So first, I made an RDD that had 0s, 1, 2, 5, 4, 5, 5, 5. Then I mapped a lambda across it that just added a key that said even or odd, depending on which it was. So here you can see in the output that it correctly classifies all of the numbers as even or odd. And then here, we used AggregateByKey with the set constructors that we had made before, the zero value of an empty set, the seek operator that can add numbers to an empty set, and the combine operator that can combine any sets. So here, you can see that the set of all observed values for even is 0, 2, and 4. The set of all observed values for odd is 1 and 5. Because AggregateByKey allows us to provide whatever we want for the zero value and the active functions, it can be used to calculate almost anything over your data. You could calculate an average over all your data by starting with an empty pair, then keeping the sum in the first part and the count in the second part of the pair. At the very end, you could divide the sum by the count to get the average. That great flexibility is going to make this an important tool in your Spark toolset. However, before you run out and rewrite all the statistical methods, check to make sure that Spark doesn't already have it. Rewriting your own average doesn't solve anything. Remember, if you need to calculate an aggregate over your data, while it is grouped in some way, but you can't formulate a single commutative associative function to do it, you need AggregateByKey. This video will cover the SortByKey transformation in PySpark. SortByKey allows you to sort an RDD of key value pairs by the key. It also provides optional arguments to set the sort order, the number of output partitions, and a pre-processing function for the sorter called a keyfunc. Let's check it out. Okay, here's our sample dataset. It's 4 pairs, a capital B with a 1, lowercase a with a 2, capital A with a 3, and a lowercase d with a 4. Now we're going to sort this in different ways and check out how the different options affect the resulting sort order. Here, we naively sorted with the default options for everything. You can see that capitals come first and lowercase come second. Other than that, there's really nothing unexpected here. Here you can see I passed false for the ascending optional keyword argument. Passing it false switched my sort order. So it's exactly the opposite of what we started out with. So here, I'm illustrating the MapPartitions optional keyword argument. Also, I'm using the glom transformation. That takes everything in a partition and puts it into a list, so that later on when we collect, we can see what the partitions looked like beforehand. So you can see when we have one partition, everything is in that same inner list. If you look at the second one, we have 3 partitions. You can see that we have one that contains capital A and capital B, then a second one that contains the lowercase a, and a third one that contains the lowercase d. In this one, we specified a keyfunc, which is kind of a preprocessor for sorting. Each key was passed through the keyfunc and then sorted. Now that doesn't change the output value. You see, we still have capital letters in our output, but it changed the value as the sorter saw it. So you can see that we have A's first, and then B, and then D. This lets you sort on just part of a key, or do some kind of normalization on the key, so that the sort turns out just the way you want. In this case, we normalized by lowercasing everything. If you're sorting data that isn't already in key-value pairs, you can use the sort transformation. Otherwise, use SortByKey to get your data in order. This video will cover the join transformation in PySpark. The join transformation is one of the best ways to combine two different RDDs. Join operates on two key-value RDDs by combining all pairs of values with the same key. A quick example will make this really obvious. So here I have two RDDs, A and B. They're both key-value pair RDDs. So now I joined them together. Because join operates on keys, the only output we get is where keys matched. So here you can see that it was the key number 2 that matched, and from the first RDD we had the value A, from the second RDD we had the value B. So our output is a sequence of pairs. The first pair is 2, the key that matched, and then inside that another pair, A, B, because those were the two elements from the two different RDDs that matched. Since join generates output for keys that match between the two RDDs, we only see one output pair. You might be wondering what happens when we do this with more than one match. Let's check it out. Okay, here we've made a third RDD, C, and it has the key 2 twice. Okay, so this might seem a little bit weird at first, because we have two pairs with 2 in them in RDD C, they have the key of 2. We have two matches between A and C. We get an output pair for each of those matches. If we had the number 2 twice in RDD A, and the number 2 twice in RDD C, then A join C would produce 4 pairs of outputs, all possible combinations of the items where the first value is from RDD A and the second value is from RDD B. If you expect to have many items with the same key, you might want to put them all in the same group. So check out the CoGroup transformation. It's similar to join, except instead of showing 2 here, it would just show one big entry for 2. It would show all of the common values next to the one entry. Another important thing to notice is how you're losing data. Any key that was present in only one of the data sets is lost. Notice in our last example how we completely lost the 3B pair, since the other RDD didn't have any keys that were 3. Spark provides the left outer join, right outer join, and full outer join. These are named after the relational database join methods. Left outer join makes sure that every key from the original RDD makes it through. If the second RDD doesn't have the key, the pair will have a none in the second spot. So here you can see that RDD A had a 1 and RDD B didn't. So you can see that there is a value for A and then there's a none for B. Right outer join works exactly the same way, but it ensures that all the values from the second RDD make it through. Lastly, full outer join makes sure that all values from both RDDs make it through. Whenever you use any of the outer join transformations, you need to make sure you can handle none outputs in the results. Also, all of the join methods take a second optional argument to set the number of partitions. Whenever you do one of these joins, you could potentially be moving a lot of data around the cluster. It could definitely be a performance bottleneck. If you're trying to speed things up, see if you can do fewer joins, or maybe you can filter your dataset down smaller before you join. In any case, when you need to combine two different RDDs by key, you can use join, right outer join, left outer join, or full outer join. This video will cover the CoGroup transformation in PySpark. CoGroup is one of a couple of transformations that allow you to combine two RDDs. CoGroup allows you to join two key value pair RDDs, just like join. However, join and CoGroup differ in the way they handle repeated keys. Let's look at a quick example. Okay, Here's two sample RDDs. First, let's join them, and then let's CoGroup them to see the differences between join and CoGroup. Okay, joined, we have two results. And that's what we expect, because RDD A has the key 2 once, and RDD B has the key 2 twice. So if we do all possible combinations there, that's just 2. Now let's CoGroup them. Okay, so we get these result iterables again, which are really helpful for efficiency, but they're really hard when you want to print stuff out to the REPL. Okay, so this time I used a map values to use the list function on each of those result iterables. So I didn't change anything, I just forced them from iterables to lists so that now we can inspect it. Okay, I deleted that previous response so that we can see all of this on the same page. So here you can see that CoGroup provided an output for each of the keys we had. For 1, it just has an A. For 2, it has an A and then also a BC. And then for 3, it just has a D. So what it's doing here is for each key, it provides a list of all the values that were seen on both sides. If you need to see everything with the same key all at once from both RDDs, then CoGroup is the right function. If you'll never have duplicate keys or you need to do an all pairs comparison, then one of the join variants is probably what you want. This video will cover the whole text files method in PySpark. Whole text files is a method on Spark context that allows you to read in a directory of text files, returning them as pairs. Each pair is of the form file name, content. Whole text files is similar to the text file method, with a couple of differences. Text file returns an RDD with one element for each line in the input text file. Whole text files returns an RDD with one element for each file. That element is a tuple of file name content. Let's look at a demo to show the difference between the two. Okay, sample input is a directory that has two files in it. Each of them have a couple lines of text. Here you can see that when we used sc.txtfile, we got out an RDD that has 5 elements. Each of them is one line from one of the files in the sample input directory. And here you can see when I used the whole text files command, I only got 2 elements in my RDD. Each of them is a pair that's the file name and then all of the content within the file. So when choosing between text file and whole text file, you need to decide whether each text file is an item or each line in the file is an item. For example, if I was generating word counts for each of my input files, then it'd be important to keep the input from each file separate, and whole text files would make sense. However, if I wanted to build a term frequency table, something that counts how often each word is seen in our entire document corpus, then text file would work just fine. Whole text file works best with relatively short files. For example, if you have a bunch of 10 gigabyte log files, whole text file is going to choke. It's going to have to read 10 gigabytes into each element of your RDD. That's not going to work out. Also, remember that parallelism can never be higher than the number of elements in your RDD. So if you had 2 giant text files, which you read in using whole text file, and then you wanted to process it on your 100-node cluster, well, 2 of the nodes would be really busy processing those files. The other 98 would sit idle. This is a reason to use text file instead of whole text files whenever you can. More elements in an RDD will let it get spread out more evenly across your nodes. You can read files in from the local file system, although it has to be present in the exact same spot on every node in your cluster, or over HDFS or any other Hadoop-supported file system. In addition to providing the path, you can also use the MinPartitions keyword argument to set the minimum number of partitions you want. Also, you can pass the useUnicode keyword argument to determine whether Python will use UTF-8 strings instead of Unicode. By default, Spark uses Unicode to be safe. UTF-8 strings are smaller and faster, so if you're sure you don't have any Unicode characters, go ahead and pass useUnicode equals false. That'll make things a little bit quicker. This video will be about Pickle Files in PySpark. Pickle Files are a way to store and load Python objects in Spark. They're named after the Python Pickle module, which provides object serialization. A common use case would be something like this. Load in some data, maybe from a text file. Process that data into some Python domain objects that model your domain. Then save those Python objects out into a Pickle file. Later, when you want to reload all of those domain objects, all that data, to do some additional processing, you would load that Pickle file. Now, instead of having to deal with a bunch of strings, the way you would with text file or something like that, you have an RDD full of objects right from the get-go. Let's look at a quick demo. Okay, so here we first made a sample RDD. This RDD contained 3 elements: a string containing the letter A, character A, the integer 1, and then a map, a dict, of the string key to the value, the string value. Then we saved that RDD as a Pickle file, named Pickle File. So now let's read it back in. And here you see, when we read the Pickle file back in, we got an RDD that's just like the first one. We didn't get strings back that then we had to parse. We didn't get JSON that we had to run through some kind of JSON parser or anything like that. We got back an RDD that has exactly the same kind of objects that we saved out, without any additional parsing. Pickle files mean that you don't have to think up a text format for your data. Without this, we'd have to convert it to CSV or JSON for your file storage, and then I guess write a parser to read it back in, and then reconstitute our objects. However, even though it's simpler in some ways, there are some things you need to think about when using pickle files. First, you need to make sure that your class is pickleable. You can check the Python's pickle docs to make sure. Basically, as long as you're serializing primitive types, like numbers or strings, etc., you're fine. And your class has to be at the top level of the module that it's in. However, nested classes or dynamically created classes might not work. If in doubt, you can always just do a small test run to make sure everything survives serialization as you expect. Also, just because you can easily serialize your domain objects doesn't mean you should. Maybe they have a bunch of data that isn't really that important. Maybe they have instance variables that aren't going to be used anymore, or are really cheap to recompute. In any case, the more data you serialize, the longer it takes to write, and the longer it takes to read. And you'll take up more disk space while storing it. Trimming your data can have a big impact on performance. Also, if you're looking for even more of a performance boost, you could try using Thrift or Avro, or something like that, instead of Pickle. Thrift requires you to write out a schema beforehand, but because there's a schema, serialization can be very quick and quite efficient. You probably want to start with Pickle and then switch when the extra performance is worth the extra engineering effort. One benefit of Thrift over Pickle is portability. Pickle files are really only readable in PySpark. If someone else is using the Java or Scala Spark interface, they won't be able to load your objects, since they're Python specific. Thrift objects can be operated on by the Thrift client library in whatever language you're using. There are Thrift client libraries for most languages. Remember, if you have objects in RDDs and are trying to figure out how to save them for a later run, check out PySpark's Pickle file. This video will cover the different ways PySpark can read data in from Hadoop input format. PySpark has a ton of flexibility with input and output. One of the ways it accomplishes that is by supporting input from any Hadoop input format. However, if you can use one of the other input methods, I would do that. The Hadoop input format interop is a little confusing and definitely complicated. Because PySpark is Python and the Hadoop input format is Java, there's going to be a little bit of extra work and some weirdness. We'll have to start worrying about types, which normally in Python is not such a big deal. However, the fact that you can do it at all is a huge feature of Spark. I'm sure that this was a lot of work when it was being implemented, because cross-language compatibility isn't simple and it's not automatic. The tricky part here, or maybe one of the tricky parts, is that there are 2 Hadoop input format APIs, and there are 2 methods for each API, for a grand total of 4 functions, 2 each for 2 things. So first, how do you know if your input format is from the old version or the new version? Well, check the documentation. But if the documentation doesn't tell you, you can always read the source. Look for references to MapRed or MapReduce so you can sort it out. Here, I'll type those out for you. So here, if something is org Apache Hadoop MapRed, that is the old API. If it's org Apache Hadoop MapReduce, that is the new API. So once you know if you have the old or the new API, that cuts down the choices from 4 to 2. So here are the 4 methods that you'll have to use, depending on whether it's the old version or the new version. We have Hadoop file and Hadoop RDD for the old version. And then we have new API Hadoop file and new API Hadoop RDD for the new version. So the key to helping you decide is whether you provide a file for the input format, like you would for a text input format, or whether you set the information in the Hadoop conf. If you set all of the information in the Hadoop conf and then let it go, use the Hadoop RDD command. If you provide a file to open, then use the Hadoop file command. Once you know whether you're using the new or old API, and whether you should use the Hadoop file or Hadoop RDD variant, you're ready to get started. Here's a quick demo. Okay, so I know I said that was a quick example. You're probably looking at this and thinking, what just happened? So let's look through each of these options individually to get a feel for what they do. Fortunately, all 4 commands have pretty much the same options. First, path. Well, I lied. They don't all have path. If you use one of the Hadoop file commands, it will have a path option. If you use one of the Hadoop RDD options, then that's going to pull information from the conf that we'll cover later, so it won't have a path. So this is the path to the file you're trying to open with the Hadoop input format. Different formats treat the path differently, so you'll need to read the documentation for your input format. Next, the input format class. This is the fully qualified name of the input format. You'll need to make sure it's available on the class path of your application. Then, the key and value classes. You can figure these out by reading the source of your input format. An input format should create a record reader with one of its methods, which will have generic type hinting that gives you the key and value classes. Next are the key and value converters. These allow you to do some work to put the key and value into the format you need. These default to none, and you probably won't need to set it. Spark has some reasonable defaults here. Next up is conf. You can provide a map of values and they get turned into a Hadoop conf, which is used by the input format. For example, the text input format lets you set the record delimiter in the conf. Finally, batch size. How many Python objects should be represented as a single Java object? If you don't know the answer to that question, leave it as 0 and the decision will be made automatically. That's probably the right answer. Okay, so sorry, I know that gets a little bit involved, it's kind of crazy, but the big win here is flexibility. There are Hadoop input formats for anything you can imagine. Being able to plug those into Spark and even the Python version of Spark is huge. I would recommend reading the Spark programming guide on Hadoop input formats before you do a lot of this on your own. There are a lot of nuances and fiddly little bits that probably aren't going to work right the first time. But when you need it, and it's great that you have it. This video will cover using Hadoop output formats in PySpark. PySpark can output data in any form described by a Hadoop output format. However, this is not the easiest API to use. If you can use one of the built-in methods like TextFile or Pickle File, I would use that instead. However, sometimes you need the flexibility to output in some obscure custom format. Well, PySpark has you covered. There are 4 methods involved in this functionality. Just like Hadoop input formats, they're split out into the old and new API and dataset versus file. Okay, so here's the old API and the new API with the method names. And then also, I included the string that you should look for in the source code if you can't find out from the documentation whether you're using the old or the new API. So in this case, if you see org Apache Hadoop MapRed in several places, that's a big hint that it's probably using the old Hadoop API. If you see a lot of org Apache Hadoop MapReduce, then you're probably using the new API, and you should use the new API methods. Newer versions of Hadoop contain both the old and the new APIs, so you can't just check what version of Hadoop you're using and figure it out from there. Once you've figured out whether you're on the old or the new API, you'll need to figure out whether you want to use Hadoop dataset or Hadoop file. The easiest way to do that is to figure out what sort of configuration is required for your Hadoop output format. If, when you call it, you need to provide a path to save the file, you should use the Hadoop file variant. Otherwise, use Hadoop dataset. You would use SaveAsTextFile for things like saving into Elasticsearch or pushing data into a database. In that case, it doesn't really make sense to say what file you're saving to. You're saving to a system. I don't know where Elasticsearch saves my data. I don't want to tell it what file to use. Elasticsearch should figure that out on its own. A Hadoop dataset invocation would look something like this. You can see that it's pretty simple. I provide a configuration map, and then a key converter and a value converter. Although this looks simple, it hides the fact that you need to pack, generally, a ton of stuff into the configuration. You'll need to read the documentation for your Hadoop output format, but you're probably going to put a lot of stuff in there to set it up. Key converter and value converter, on the other hand, can normally be left as none. You don't even need to pass them. They'll default to the normal Spark Java to writable converter, which will probably work. Now, if you're saving a file, if you're going to output maybe a JSON text file or something like that, and for some reason you've decided to use a Hadoop output format instead of the significantly easier text file, then you probably want to use the SaveAsHadoopFile method. This method has several more arguments, but you don't have to put as much into the configuration. Let's look at a sample invocation. Let's talk through each of these options. First, the path. All right, this one's pretty straightforward. That's just, where do you want this file to end up? Now that path is going to be interpreted by the output format you use. So read the documentation in the output format to make sure you understand how it wants to be told where to put the file. Next is the output format class itself. Notice that you pass it as a fully qualified name in string form. Make sure that this is available on Spark's class path or you'll have a problem. Next up are key and value class. Here, you can either provide the key and value class, picking from Hadoop's many writable classes, or you could leave them as none and let Spark figure it out. Personally, I'd leave it alone unless Spark gets it wrong. Then you have the key and value converters. Just like key and value classes, if you don't pass that or leave it as none, it'll default to something that generally works. In fact, if you're passing a value that it doesn't know how to convert, it might be simpler for you to just do a map task that converts it ahead of time, rather than getting into the little bit more complication of writing a key converter or a value converter yourself. Okay, next up is the conf. This is where you would put extra configuration options for your output format. You would pass it in as a map, or a Python dict. Finally, the compression codec class. This defaults to none. If you want to provide a class, Spark will use that file to compress your output. You can often also set the output compression in the configuration. Okay, sorry, I know that this was a little bit of a complicated video. The Hadoop input format and Hadoop output format stuff is some of the more complicated parts of PySpark. However, they offer you unlimited flexibility, especially if you're willing to write a little Java yourself from time to time. My advice is that if you think you might need them, go ahead and read the programming guide and the API docs in detail. There's a whole lot going on here, and it's going to take a little bit of work on your part to get it working. However, like I said for the input formats, when you need it, you need it. This video will cover broadcast variables in PySpark. Sometimes you need to share a dataset with all of your executors. The obvious way to do this is to set it as a variable and then reference that variable within the processing function for your task. That would look like this. Okay, this works just fine when you've only got one stage. However, what if we had a process like this? Okay, this example still works. It produces the output we expect, but it hides an important issue. Our important data variable was serialized and sent with the task info for both stages. Here we had a map, and then a repartition and another map. Because repartition will have a shuffle, those two maps are different phases. Spark sends the task info for each stage separately, which includes serializing and sending any variables that need to be present. Now, of course, in this case, sending the number 21 twice probably isn't going to break us. However, what if our important data was a gigabyte of index data? At that size, it starts to matter how many times you send it. Because this happens more often than you might think, Spark provides something called broadcast variables. Broadcast variables are a way to efficiently move large amounts of data out to your executors and have them remain between stages. If you only need the data for one stage, broadcast variables aren't a big help. They are distributed with an efficient peer-to-peer system between the nodes, which is a little bit faster than the general data distribution system, but it isn't going to change your world. However, if you have a big dataset that gets referenced in many different steps, a broadcast variable lets you send the data just once instead of once per step. That could be a huge deal. Additionally, broadcast variables are really easy to use, so there's really no reason not to use them if they can make your stuff a little bit faster. Let's look at a quick example. So here I've created a broadcast variable that holds the value 21. Note that we create broadcast variables using a method off of the Spark context that you should already have if you're doing a Spark job. So now, instead of important data being 21, important data is a PySpark broadcast variable. We can still get the value out of it by asking for value. And you can see here that we're still getting the expected values out of our map task, but we're using importantData.value. Now, you want to pass it around as important data. If at some point you pull out importantData.value and start passing that around individually, that's going to defeat the whole purpose of what we're trying to do here. We don't want to pass around the value. We want to pass around the broadcast variable and ask for the value at the last possible second. One important thing to remember is that broadcast variables are read-only. You cannot change the variable in one place and expect everyone else to see it. These aren't magic, they don't talk between executors, they're not synced every time you make a change. You create it in the main driver program, you call it a broadcast variable, and then it's sent out to the executors. That's a one-way change. Don't change it in the executors. It's going to cause problems, it's not worth it. That's the wrong solution for whatever you're trying to do. When you're done using a broadcast variable, before you're done with your entire workflow, you can call unpersist on it. This will cause Spark to delete cached copies of the variable, reclaiming memory you might need for other things. Remember, if you need to pass a large block of data out to your executors, and you'll use that data in more than one stage, broadcast variables are going to be a huge help. This video will cover accumulators in PySpark. PySpark makes it easy to get output from your jobs. In fact, if you couldn't get any output, Spark wouldn't be very useful as a processing framework. But sometimes you want to get two different kinds of data out of your job. First, the main data you're processing, but then also some kind of metadata, maybe some job-specific counters or timing information, or some debug info during the development process. Having a side channel to return this kind of information allows you to keep these two different kinds of data separate. The alternative would be some kind of metadata chunk in every output file. Then later on, you'd have to go over all those output files and pull the metadata out and generate a report. That's doable for sure, but why mix together data if we don't have to? Well, let's look at accumulators. Accumulators are a type of variable you can always add to, but only look at in the main driver of the job. Let's look at a quick example. Okay, so let's look over what we've done so far. First, I set up a new accumulator named evens that starts with 0. Next, I made an RDD called numbers that has the numbers from 0 to 9. Lastly, I made a function, inc_and_report, inc for increment. So this function takes a number, x, and then if that number x is even, it increments the evens accumulator. And then, whether it was even or not, it returns it incremented 1, so 1 higher than it came in. Here you'll notice I had to use the global evens. That's because if I don't have that, since I assigned to evens, it's going to become a local variable within this function, and then it won't be able to see the top level evens, which is an accumulator, and it's going to cause an error. So this global evens tells Python, hey, even though there's an evens inside this function, don't make a local evens. Make that the original evens, the global evens. So that's a little tip, otherwise it's going to cause you problems. Okay, so here you can see I got 2 different kinds of information out of my workflow. First, I got my actual results. You can see that I have the numbers 0 through 9, each incremented once. Now I have the numbers 1 through 10. Nothing new here. But I also got results from my accumulator. Here, it's the count of even numbers. This count came through a side channel, and the eventual recipients of my primary data don't need to see it. The people who are receiving my list of numbers 1 through 10, they don't need to know that I counted how many evens there were. This can be a great benefit for people maintaining the pipeline or tracking statistics. Now, a couple of potential gotchas for accumulators. So here, I ran the same map task over numbers and collected the result, and I got the same result, 1 through 10. But look, evens.value is now 10 instead of 5. Because I have the same accumulator from before, it continued to accumulate. It didn't get reset just because I reran the map task. Also, in addition to me rerunning transformations, sometimes Spark will rerun transformations within a workflow. Sometimes it could happen because there's a failure, so Spark restarts something. Sometimes it happens because Spark didn't know you wanted to keep the data around, so it throws it away, later realizes you still wanted it, and recalculates it. In each case, you could get double, triple, quadruple counting for things in your accumulator. Counting inside an action is guaranteed to be once only. Counting inside a transformation has no guarantee. The ForEach action is often used to make sure everything is pushed through an accumulator. Another gotcha is that Spark is lazy. Okay, so here, I've reset my evens accumulator to 0. And here, I did numbers.map inc_and_report. So what do you think the value will be when I check evens value? It's 0. So this shouldn't be a surprise if you remember that transformations are lazy. Spark never runs transformations unless an action forces them to run. So, even though this transformation would increment evens 5 times in this case, since no one forces it to run, it doesn't run. So, as long as you keep in mind these couple of gotchas, accumulators are really helpful. If you want to accumulate something other than numbers, Spark allows you to create your own custom accumulator types. You aren't limited to what PySpark provides. This video will cover custom accumulators in PySpark. Accumulators are a great way to get information out of a task via a side channel. However, the built-in accumulator only lets you accumulate numeric data. What if you want to accumulate something else? Well, you set up a custom accumulator. For example, maybe we want to keep a set of all the IDs we've seen during a job. Now, of course, we could already do this with the distinct transformation. But maybe when you're processing this data, it has an eventual destination that doesn't want to know this ID set. So we're going to try and produce this and then return it via a side channel. Here's how we do it if it were our main data. Okay, not hard, but now we have to return this set as the result from our job. How could we do this with a custom accumulator so that we could still return what we wanted to and have this available on the side? Well, custom accumulators need to know about the 0 value and have a way to add in place. You'll also need to subclass PySpark.AccumulatorParam. A custom accumulator that accumulates items into a set would look something like this. Let's talk through how this custom accumulator works. First, we inherited from AccumulatorParam. Then, we defined the 0 value and the add in place. So, for a 0 value, we make an empty set, then we add the initial value to it, and then we return that set. For add in place, given two sets, we union them together. Union is a method on Python sets. Now let's look at how we'd use it in the job. Here, we've made an instance of our custom accumulator. We named it IDsScene, and we called SparkContext.Accumulator like normal. We don't really have an initial value, so I'm going to pass in none. If that shows up at the end, we'll know that that's something we can ignore. Also, I've passed in an instance of the setAccumulatorParam. Okay, here I set up a custom function, inc_and_note, for increment and note. I provided a global declaration for IDsScene. That tells Python, look for the value of this variable outside of this function. If you don't do that, it notices that IDsScene gets assigned to within this function, and it will create a local IDsScene that will shadow the global IDsScene. So by telling Python that it's global, we'll avoid that hassle. Then, after adding x to IDsScene, we're going to return x plus 1, because the main channel here is incrementing. It's only the side channel that's keeping track of all the IDs we've seen. To execute this, then we'd call ids.map inc_and_note.collect. Now, I'm not going to call this, and the reason is that we're going to get an exception. The reason we'll get an exception is that we've only defined the class in the REPL. So when PySpark tries to use Pickle to send this accumulator to all of the executors, it's not going to work, because when Pickle tries to find that class, there is no file for it to load from. It's only been defined here in the REPL. So we'll just have to trust that this works. Hopefully, that provides you a little bit of insight into how to make a custom accumulator. First, be careful if you're doing something exactly like this where you're trying to keep track of membership. I'm keeping every input element's ID. On a very large data set, this could consume a lot of memory. It could consume all of your memory. If you need to get a membership count, you could use something like a hyperlog data structure. If you need membership testing, maybe you should construct a Bloom filter. Anyway, this is just a toy example to demonstrate how you would accumulate. This is not a good example for how you should actually accumulate IDs. It's going to use all your memory and crash your job. Just like with normal accumulators, custom accumulators have a couple of gotchas. If accumulations are happening in transformations, there's no guarantee it'll only happen once. If you run them in actions, there is a guarantee that it will only happen once. Also, transformations are lazy, so accumulators and transformations that are never forced to run won't run. If you're getting empty results when you expected something else, make sure you have an action to force the workflow. PySpark is a distributed processing system. When you load a dataset, the data is distributed across all of the processing nodes. You can use the glom command to see what the different partitions are. Here's a quick example. So here, when I made the RDD, I asked for 3 partitions with num slices equals 3. After that, I used the glom command followed by collect to print out the contents of my RDD. But you can see that they've been wrapped, so I have my RDD, which is the full list. Within that, there's 0, 1, 2, 3, 4, 5, and 6, 7, 8, 9. Each of those is its own partition. Glom put them into the sublists like that. Now, I wouldn't do this with a large dataset. It'll probably run out of memory since it loads an entire partition into each of those elements. But with a small exploratory dataset like this, it can give us some valuable insight into our partitioning model. When repartitioning, by default, Spark would use hash partitioning, which means that it hashes each element, then sends it to an executor based on the modulus of the hash value when modulo against the number of nodes in your cluster, or the number of partitions that you asked for. Now, this parallelize, when we asked it for slices, it looks pretty clear that it just tried to make 3 roughly equal slices, and this isn't hash partitioned. You wouldn't expect to see 0, 1, 2 all in the same partition. This is clear that it just partitioned it by order. When partitioning, it's good to think about what kind of partitioning strategy you had. The goal for it is to equally distribute the elements across your cluster. So, parallelize, even though it uses an order-based partitioner instead of a hash partitioner, still did a good job of distributing things evenly. I have 3, 3, and 4 elements. So that's a pretty good job. That's as good a job as it could have done. Another thing to consider is the size of your inputs. If you have 100 inputs, but between 2 of them, they're 1,000,000 times larger than the other 98, you aren't going to get a nice even distribution. Whenever possible, you want elements that are at least the same order of magnitude. This is important because workflows have to wait at each step for the slowest executor to complete. If 99 of your 100 nodes finish in 5 seconds and the last one takes 10 minutes, then that step will take 10 minutes, and you'll tie up all 100 nodes for those 10 minutes. In the previous example, if you had 2 inputs out of 100 that were significantly larger than all the others, and processing time was proportional to the size, then those 2 elements would make the whole step slow. Anything you could do to break them down so that they could be evenly distributed would speed things up. Another important concept in partitioning is moving data as little as possible. Spark remembers when data is partitioned and how it was partitioned. With a little attention, you're often able to partition once, move data all around the cluster, and then use that partitioning scheme several times. This avoids several shuffles, which will save a bunch of runtime. Shuffles are almost always the slow part of your processing pipeline. Paying attention to partitioning to prevent extra shuffles is an important part of performant Spark programming. The rules for shuffles and partitioning are: 1. RDDs remember if they've already been partitioned. 2. A shuffle will see that an RDD has already been partitioned and reuse that partitioning when possible. A case where that would be possible and impossible is if you have something that's already been partitioned into 3 partitions, and you ask it to repartition into 3 partitions. It will say, oh, look, we've already got 3 partitions. We don't need to repartition again. But if we had repartitioned it to 3 partitions, when it had started out with 2, it would say, oh, they're asking for 3 and it's got 2. We're not going to be able to reuse that. We're going to have to reshuffle and repartition. A shuffle with 2 RDDs, like a join, will use the partitioner of one of them, assuming they have one. Given all of those rules, the game is to set up situations where RDDs that you have to join are already partitioned identically. That means that the data is already co-located on the nodes, and you can skip the shuffle step. Let's look at some examples. I know this is a little confusing at first. Let's assume we have 2 RDDs, A and B. Both of these RDDs are key value pair RDDs. In this case, there will be one shuffle when A and B are joined. The follow-up reduce will see that we are already partitioned by key and run without another shuffle. So this will cause one shuffle even though there's 2 reduce-like operations. So this looks very similar, but it has a key difference. First, there's a shuffle when A is joined to B. Then we map a transformation across the resulting RDD. Then we reduce by key. This will cause 2 shuffles. The join causes a shuffle, then the map loses the shuffle information. Spark has to forget the information because the map could change the keys and make the partitioning incorrect. Because we lose the partitioning information in the map, when we get to reduce by key, we have to do another shuffle. So this is almost exactly the same as the previous example. In this case, A is joined to B and there's a shuffle. Then we map across the resulting RDD, but this time we give Spark a clue. We say, hey, this is not going to mess up the partitioning. In this case, that would probably mean, since it's a key-value pair, and we've partitioned on the key, maybe we're not doing anything to the keys, we're leaving them all the same. So we can tell Spark, hey, don't worry about it, the partitioning is still correct. So then, when we get to ReduceByKey, Spark looks at the RDD, sees that it has already been partitioned by key, and just uses that. So this, even though it does the exact same work as the example before it, only has one shuffle instead of two. So it would expect to run significantly faster. So here's our last demo. Here, A is joined to B, which causes a shuffle. Then we use a function, a transformation, called MapValues. MapValues takes key value pair RDD, but only applies the function to the values. Because it does that, it knows that it hasn't messed up the partitioning. Then, when we reduce by key, it sees that it's still partitioned, and it doesn't trigger another shuffle. This is also a one shuffle example. So out of our 4 examples, the first one is 1 shuffle, the second one is 2 shuffles, the third is back to 1, and the fourth is back to 1. So that might be more than you wanted to know about what triggers shuffles in Spark, but this is really important for speeding up slow workflows. Shuffles are expensive and slow. If you can make a small change or pay attention to have 1 shuffle instead of 2, that's a big win. In other versions of Spark, you can provide a custom partitioner when reducing or repartitioning. That's a lot harder to do in PySpark. You can do it in RepartitionAndSortWithinPartitions, possibly the longest named transformation in PySpark. But in general, that's a lot harder to do in PySpark than it is in the Java Spark or Scala Spark APIs. You would use a custom partitioner when you wanted to later operate an entire partition with MapPartitions. That way having custom partitions would make that work more efficient. You probably don't need to think too much about partitioning when you're getting started, but it can be a great way to squeeze some extra performance out of your pipeline. Spark recommends 3 to 4 partitions per executor, just to make sure you have enough to spread your data around. When you're just getting started, the Spark standalone cluster is easy to set up. If your organization already has a Yarn or Mesos cluster, you should probably use that instead. Spark runs just fine on those clusters. Otherwise, if you have some computers and just want to get started, the standalone cluster is a simple way to get going. A Spark cluster consists of a master and 1 or more slave nodes. In this demo, I'll cover how to start a master, start some slaves, and automate the process. I won't cover the many configuration options that are present for the standalone cluster. When you get ready to set this up for yourself, check out the excellent online documentation. The settings allow you to control how much memory you use, how many cores run on each executor, where to store log files, what port the UI should listen on, and a bunch of other things. Reading through all the settings at least once is worth your time. You probably won't need most of them, but I'll bet you find something that helps you out. The Spark standalone cluster is the simplest way to get started. If you want more advanced job priorities, queues, user limiting, etc., you should check into Yarn or Mesos. If you aren't sharing the cluster, or are just doing some prototyping and dev work, the standalone cluster is easy to get working. First, let's start a master. So here, I'm inside the directory that you get when you unzip the Spark download. So to start a master, you use sbin startmaster.sh. That starts up the master. So here we can see output from the master. One important thing to pull from this is the Spark master URL. You can see that here. I'm going to copy that for later. Now, let's start a slave. When you start a slave, you need to provide it the master URL so they can communicate. You'll also want to correctly name the file when you execute it. Now we can also see the output from the slave. And down at the very bottom, you can see that we successfully registered with the master. Now, stopping a slave. Okay, we stopped it. That was the simplest, most boring Spark cluster you could possibly have. But you probably don't want to log in to each slave and start it like that. Instead, you can set up a file in the Spark directory called conf/slaves. Each line of that file should be the host name of one of the slaves. Once you have that set up, you can use the command sbin startslaves.sh. This is what was messing up my tab complete earlier. This will start all the slaves mentioned in your new config file. It'll default to just starting one on localhost if you don't have a conf slaves. There is also a stop slaves There's also a start all and a stop all. The standalone cluster is resilient against slave loss. Losing a slave won't really hurt it. Now obviously, you lose the processing power that that slave contributed, but it doesn't bring your cluster down. Losing the master node is a different story. Losing the master node will stop all new jobs from being scheduled. To work around this single point of failure, you can use one of two high availability setups. First, you can set up standby masters through Zookeeper. When the main master dies, one of the standby masters can pick up its state and take over administering the cluster. The failover process takes a minute or two, but then you'll be back up and running. Alternately, you can use the single node recovery with local file system option. This works by writing the master state out to disk. Whenever the master is started, it checks the disk to see if there's any old state there from before, allowing it to resume if it died. This doesn't help if the entire node that the master is on disappears, but it does help if the process died for some reason, and the node is still okay. If you're wanting to get a cluster set up quickly for some dev work, or just have one user, the Spark standalone cluster is a great choice. It's simple and it gets the job done. Once you have your cluster up and running, you run jobs against it using the spark submit.sh script. Spark submit has a bunch of options to get your job set up just right, so you'll want to read the documentation. Basically, it'll package and ship your job to the cluster. I'll type out a simple invocation, but I'm not going to run it because I've turned my cluster back off already. The bare parts here are spark submit, who are we submitting to, what are we submitting, and then an optional argument that myworkflow.py would read. Mesos is a popular open source cluster manager developed under the Apache Software Foundation. Mesos lets you share one cluster between many different users and applications. It's also easy to run Spark on top of an existing Mesos cluster. The first time you try to run a Spark job on a Mesos cluster, you'll need to make sure that Spark is already present on all the nodes, or that it's present somewhere Mesos can download and install it from. Check out Spark's running on Mesos docs. Spark, Hadoop, Kafka, and many other applications can all run on and share the same Mesos cluster. One big cluster is generally more efficient than several specialized smaller clusters, because you never waste resources assigned to an underused cluster. This is one big advantage of Mesos over the Spark standalone cluster. When you run a Spark job, you get resources from the Mesos cluster. When your job ends, those resources go back into the main cluster for everyone else to use. You are only consuming the resources you're actually using, which is efficient. You're also able to run multiple Spark instances at the same time, with different amounts of resources assigned to each. Setting up Mesos is well covered in the Mesos documentation. If you're thinking about using it, spending some time learning to set it up and getting acquainted with it is going to make things a lot better for you. I'm going to assume you already have a working Mesos cluster in this explanation. When you launch your job in the fine-grained mode, which is the default Mesos mode, the Spark driver program will ask the Mesos cluster for resources. Then the cluster responds with the name of the resources that were assigned to the Spark job. At that point, Spark starts up slaves on each of the assigned machines and runs the Spark job. While the job is running, it's a little like you have your own standalone cluster, except that it gets thrown away as soon as the job is finished. You don't need to worry yourself about setting it up or tearing it down. Now, the downside of setting up a new Spark system for every job is the overhead. If latency matters to you, you may want to check out the coarse-grained mode. In the coarse mode, a mini Spark cluster is set up and then left running. This greatly lowers the overhead of running a Spark job, but it means that you're permanently tying up the resources. Permanently tying up the resources was a problem, and that's why we considered Mesos to begin with. So now we're going to tie up the resources inside Mesos anyway? No. In coarse mode, Spark can do dynamic sizing, so it can dynamically change the number of executors. If it isn't using all of them that it currently has, it can give them back. Then it can re-request them when it gets busy. This gives you the best of both worlds. Low latency, because the main master is going to stay online, but less waste, because when you aren't using executors, they get returned. If you're going to use the coarse-grain auto-scaling, check out the Mesos Shuffle service. This is the daemon you'll want to run because it helps with Spark shuffles. Without it, losing executors could mess up the shuffle because shuffle data is stored on the executors. Mesos is a great cluster manager. If you already have a Mesos cluster, running Spark jobs on it is dead simple. Use the Spark submit script and just point it at your Mesos cluster. If you don't have a cluster yet, you'll want to compare Mesos and Yarn to get a feel for what they offer. Mesos runs many different kinds of apps with a Docker-like containerization setup if you want it. Yarn has a lot of very fine-grained job priority and resource allocation settings. It's also more integrated with the Hadoop ecosystem. The choice is yours. Yarn is the next generation cluster manager from the Hadoop project. With Yarn, Hadoop tried to separate cluster management from the actual MapReduce application that is Hadoop. This means that you can run other applications like Spark on a Yarn cluster. This can be a great way to introduce a little bit of Spark into an otherwise Hadoop-intensive organization. This is how we started using Spark where I work. Running a Spark job on an existing Yarn cluster is as easy as using the Spark submit script in your Spark install directory. This would be an example invocation. You might notice that here, we don't say where the Yarn cluster is, we just say Yarn cluster. That's because Spark reads the config from your Yarn configuration directory, which you'll have to configure. Also, make sure that either the Hadoop conf dir or Yarn conf dir environment variable points to your Yarn cluster configuration files. Those files contain everything Spark needs to know. Yarn has a rich and involved set of schedulers to decide what jobs run and how resources are allocated. This richness is one of the biggest reasons to set up a Yarn cluster for your Spark workflows. If several different teams are all sharing the same cluster, Yarn can be a great way to provide equitable access for all. I will note that personally, I've had some trouble with Yarn's fair scheduler, where it preempts my executors. Basically, the fair scheduler can be configured to let you use more than your fair share. Then, if someone else shows up that wants that extra part, just those extra bits are killed and given to the other user. This causes big problems with Spark, which has to go back and recompute data that was on the executors that were just lost. Preemption can be turned off in the config, and you might want to do it, at least for your Spark jobs. Also, debugging can be kind of tricky in a Yarn cluster. The logs end up all over the place. Fortunately, Yarn provides a command to gather all of the logs back into one spot. This will dump all the logs from the job with ID, app ID, into standard out, so you probably want to redirect it to a file. If you have a lot of executors, there'll be a lot of output. I normally scan through it for keywords. Personally, it's generally the exception keyword since I'm trying to figure out why something died. A Yarn cluster provides a lot of control, but it can also require a lot of configuration and maintenance. If you don't need all of the scheduling control, Mesos or the standalone cluster might be easier. Whenever you run on a cluster, you need to figure out whether you want to run in cluster or client mode. Now, depending on whether you're using PySpark or Spark, and which cluster you're deploying to, these may not both be available. Let's look at the differences between these two modes. First, client mode. In client mode, the Spark driver program runs in the client. The program runs on the computer requesting the job. That means if you submit from your laptop, the Spark driver program lives and runs on your laptop. The master that gets started up in the cluster is only in charge of getting resources and communicating those resources back to the client. The client is the task you run to get things started. Spark submit executes the client on your computer. Then the job is organized and runs from whatever computer started things. The upside for this is that the driver prints and logs messages right on your computer. Also, you can stop the job at any time by killing the client. You have more control over the client's environment, obviously, because it's your laptop. Unfortunately, you also have to let the client run for the entire job. Also, if you have to pull lots of data into the driver, it has to leave the cluster and make its way out to your computer. That's often a slower connection than the connections within the cluster. The other option is cluster mode. In cluster mode, the client program just packages everything up and ships it to the master. The master runs the driver program and communicates with the executors, all within the cluster. The client program will return almost immediately, since it only sends the info and then dies. In this case, prints end up in the log somewhere, not at your terminal. You'll have to use the web UI to track the process of your job. In this case, the driver takes resources from the cluster instead of your computer. If you're running several jobs simultaneously, this might be your only option. Your computer may not be able to handle all of the memory it would need for the driver for many programs. In general, I have found cluster mode to work more reliably. Being able to spawn jobs and then continue my work is nicer than leaving the jobs running in the background on my computer. Also, if you have to restart your computer, say due to a Java update, it would kill all of your jobs, assuming you're in client mode. Client mode had more class path and dependency issues for me personally, but those are almost entirely dependent on your particular setup. When you're just getting started, client mode does provide more output and log messages while the job is running, so it might be nice to start there when you're doing something new. Otherwise, you have to hunt those messages down deep within your cluster somewhere, which can be kind of difficult. The Spark project describes Spark streaming as an extension of the core Spark API that enables scalable, high-throughput, fault-tolerant stream processing of live data streams. Basically, Spark streaming provides a lot of the machinery necessary to push near real-time data through a Spark workflow and store it to HDFS or a database. Spark streaming is a large topic with lots to learn. With this video, I'm just hoping to show you enough to know if you want to learn more. I don't have time to provide an exhaustive guide to a large involved topic. Basically, Spark streaming takes a live data stream, breaks it into chunks, and runs each of those chunks through a Spark topology. You can configure the chunk time, and you're also given some tools to remember what happened in previous runs. The central abstraction of Spark is the RDD. The central abstraction of Spark streaming is the discretized stream, or dstream. A dstream is a series of RDDs, one for each discrete time chunk. You can think of a live data stream like a beer tap that is constantly running. The dstream is the bartender that puts mug after mug under the tap and then slides the mugs down the bar to the waiting patrons. A constant stream of beer isn't useful for someone trying to have a beer. A discrete chunk of beer in a mug is just right for consumption. In the same way, the dstream converts a stream of data into chunks that Spark is comfortable operating on. Most of Spark's transformations already work on dstreams. You can also get a couple of new ones that remember what happened before, so you can aggregate across time. Let's check out a really quick example so you can get a feel for how things work. First, we import the streaming context. We're going to wrap our original Spark context in a streaming context to upgrade its usability. So here we've created the new and improved streaming context from our original Spark context. The 1 here is the batch interval, so I'm running a new batch every second. There are some trade-offs here. The smaller you make your batches, the more quickly you'll receive output, but the less efficient it will be. If you can afford to wait 5 or 10 seconds between batches, you probably should. That'll be less bookkeeping for the Spark process, and you'll have higher overall efficiency. However, if it's important to see results immediately or as soon as you possibly can, try adjusting this number down, see how it works. Here we make a text file stream input. This will dump any new text files in the given directory into our system. This is great for watching for new input from other processes. They just have to write their output to a given directory. Okay, this is a simple word count implementation. I start with my input stream, and then I flat map a lambda across it that splits by spaces, so now I have just words. Then I map, turning each word into a key value pair that has word as the key, and the value is 1. Once I have that, then I reduce by key and add the values together. So that means for each word, I'll just add up the counts. They start with 1, so each time I've seen the word, I'll be adding 1 more to that total. So my final output here, counts, is going to be pairs of word, comma, the number of times we saw that word. Now we output counts somewhere. And in more of a production implementation, we would probably be writing this to another directory, maybe writing it to a queue, possibly saving it to a database. Here we're getting every second output. Let's put something into that directory. And there you see the output. We were able to split it up, and it was processed right in time. Because there's nothing new, we're not outputting anything else. So that final SSC start is what kicked off the streaming process. Up until that point, we were just describing the job. Here you can see that, for the most part, Spark streaming doesn't radically change your programming experience. It gives you a couple of new input types, make D streams instead of RDDs, and then everything works just about like normal. If you need some kind of real-time processing system, check out Spark streaming. This is just a taste of what you can do with it. The Spark documentation has several more great examples. Most of Spark is happy to operate on data of any shape. However, sometimes your data already has a strong schema, and operations could be more efficient if Spark knew about it. Spark SQL and its data frame abstraction were written for just this case. Spark SQL and the data frames are going to feel very familiar if you're used to R or some of the statistical computing packages in Python like pandas. Spark SQL also lets you load data from a variety of sources. Once you've loaded it, you can either use the DataFrame API or SQL to query and get results from it. First, let's talk about the various data sources Spark SQL supports. Also, for pretty much any data source, there's an equivalent save method that lets you write results back out in that format. The simplest kind of input is JSON. If you have a JSON file full of similarly schemaed items, you can read it in with the read.json command. Let's look at a quick example. First, we created a SQL context from our original Spark context. This wraps it with some new functionality. Now we're going to read a sample JSON file. This is the file that we're reading. It has one JSON object per line. Each of them is a map with keys and values. So now that we've read it in, let's make sure that Spark SQL correctly read it. Let's check what it thinks the schema is. ID is a long, name is a string, and price is a double. Yeah, that sounds about right. And here we can see 1, 2, 3, 4, green, yellow, blue, red, and several prices. Yeah, that looks great. This command created a data frame with an inferred schema. Note that you could also call the JSON reading function on a whole directory of JSON text files. In addition to JSON, you can also read Parquet files. Parquet is a data serialization format used in many different data processing libraries. It's common in a lot of the Hadoop ecosystem. Writing and reading Parquet files is really simple. Plus, the data format is self-describing, so you don't have to worry about inferring schema, like you might with JSON. Spark SQL can also pull data in from an existing Hive installation, or through a JDBC connection. Once you've got the data, you can operate on it using either the API or SQL. Let's look at the API first. So here, we filtered and said show us everything where the price is more than $12, and then select only the name column, and then show us what we've got. This API lets you string together method calls like you would in R or Pandas. Spark SQL also lets you write SQL, as you might have guessed. That same query would look like this. So there you see that we had to register it as a temporary table, and then we just wrote a SQL statement that's selected from it. This was the same as our API example before, so we wanted only names, and we wanted it wherever the price was greater than or equal to 12. So they do look a little different because we collected instead of showing it, but you can see that these two approaches produce equivalent results. There's a lot of very interesting functionality in Spark SQL. If you're dealing with structured data, or if you have lots of data tied up in an existing Hive cluster, you should definitely check it out. It integrates nicely with the rest of Spark, so it shouldn't be hard to mix a little in where it's helpful. Also, the machine learning library uses data frames, so learning them here will help you there also. Spark ships with a useful and comprehensive machine learning library. All of the algorithms included in MLlib have been architected to be scalable and distributed. That means that some of the algorithms you're used to might be absent or work a little bit differently than you're used to. The upside is that your machine learning can take advantage of your large cluster. Writing your own distributed and scalable machine learning algorithms would be a lot of work. Using Spark's ready-made library will save you a lot of time, bugs, and frustration. The first problem you'll run into is the two namespaces. So here you'll see the two namespaces are spark.mllib and spark.ml. Spark.mllib is the original. It has the original API built on top of RDDs. Spark.ml is the second generation. It has a higher level API built on top of data frames for constructing ML pipelines. Spark.mllib, old, low level. Spark.ml, new, higher level, works with data frames. In general, you should use Spark.ml when you can. The old version will stick around, but why use lower level unless you have to? If for some reason you absolutely cannot use data frames, MLlib would let you go ahead and use RDDs, but it's hard to imagine a situation where that would be the case. Using either of these libraries from Python will require NumPy 1.4 or newer to be installed on all of your cluster. We'll be using the higher level Spark.ml for the rest of this video. Spark ML is built around the pipeline abstraction. The pipeline has several players. First, the data frame. The data frame is where your data lives. It can have different types of data, labels, and even predictions. Next up are transformers. A transformer transforms one data frame into another. The most common example would be an ML model. It takes a data frame with features and returns a data frame with features and predictions. You could also have a feature transformer that normalizes a feature, converts it to classes, removes illegal values, or in some other way prepares it for later models. The next player are estimators. An estimator is something that can be trained on a dataset to produce a transformer. The most obvious example is a machine learning algorithm that is trained to produce a model. The algorithm and associated machinery is the estimator, which, when trained, produces a model, and the model is a transformer. These are all tied together by the pipeline. It lets you chain multiple transformers and estimators together into a unified workflow. You'll also want to get to understand parameters. One of the big advances of Spark ML over the Spark MLlib package is the unified system for specifying parameters. All Spark ML transformers and estimators use the same system for setting parameters. Now, let's look at one of the example pipelines from the documentation. Here you can see that we're creating a logistic regression pipeline. We start off by making documents. Then, we configure a machine learning pipeline, which consists of the tokenizer, hashing TF, and a logistic regression model. So here, the tokenizer breaks it out into words. Hashing TF takes those words and turns them into a feature vector. Lastly, the logistic regression node is what does the modeling and learning. You can see here, once we fit it, we now have a model. The model is a transformer. Before that, the pipeline was an estimator, because an estimator is fit to a dataset to produce a model. Now we have some test data. We take that test data using the model that we already trained, and we transform the test data to make the predicted data. Then we pull some data out of the prediction and print it. Machine learning and the Spark machine learning library are big, interesting topics. You will definitely need to do reading on your own to understand how to correctly apply the algorithms and models. A little bit of reading will save a whole lot of frustrating experimentation. Machine learning can help assign labels to input, put into groups of similar objects, predict how much users will like an object based on past predictions, and tons of other things. It's a deep subject that's a lot of fun to learn about. Spark's ML libraries are really useful, and being able to throw something together quickly will be very impressive to your boss or stakeholders. This is nice to have in your back pocket. Spark is a great piece of technology. If you want to keep learning, the best place is the online Spark documentation and the mailing list. Those will both stay up to date and have significantly more depth than I've been able to cover in these videos. In particular, I was only able to briefly touch on Spark Streaming, Spark SQL, and Spark ML. Those are each huge topics and could have their own video series. I didn't even mention the graph libraries or other interesting tools being developed for Spark. O'Reilly also offers a video course on Spark, which has a lot of great examples. It isn't Python focused like this course was, but it'll still be very helpful. If you like to learn from books, I know that there are at least 2 good Spark books. Learning Spark and Advanced Analytics with Spark are both great. They helped me get a better idea of how all the pieces fit together. Lastly, if you're looking for proof of your learning, O'Reilly offers a Spark Developer Certification. This will validate your experience to your employers. Wrapping up, let's put it all together. The workflow I normally use when working on a Spark problem is 1. Read the data into an RDD. Then, use transformations to change that RDD into other RDDs, and then finish with an action to force all of the previous transformations. Once things are working, I start to look at how I could improve performance by minimizing the number of shuffles, caching datasets I'll reuse, and using broadcast variables. If I've got machine learning in my dataset that I need to do, I'll check to see which algorithms are available in MLlib. I'll test a couple different ones on some test data to see what gives the best results. If I've got a streaming data problem, then Spark Streaming is the obvious solution. If I've got data coming from a database, Hive, Parquet, or JSON, Spark SQL is going to make things a lot easier. Spark is an exciting piece of technology with a vibrant community. I expect it to continue growing, and along with that growth, there'll be more and more great guides, blog entries, books, and video tutorials. At the end of the day, you won't be able to learn anything without doing. Start coding, making mistakes, building cool stuff, and having fun. Spark makes it easy to do things that were impossible 10 years ago. We're living in the future. Also, personally, I'd like to say thanks for sticking with me. I hope you really enjoyed this series. If you enjoyed it, please reach out. I'd love to hear from you. Thanks.